Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, the universe speaks softly, and even the strangest discoveries are invited to slow down for the evening. Tonight, we are visiting a world that seems to have slipped into astronomy by mistake. Its name is WASP-193b, and by all reasonable expectations it should not exist in the form we see it. It is a planet so light for its size that scientists compared it to cotton candy. A giant world larger than Jupiter in width, yet astonishingly thin in substance. A place that appears puffed up, swollen, and improbably delicate while circling its star in the harsh conditions of deep space. Now, planets are usually quite cooperative things. Rocky planets tend to be dense and sturdy. Gas giants tend to be massive enough to hold onto their thick atmospheres. Even the unusual ones often follow at least a few rules. But every so often, the cosmos places something on the table that makes astronomers lean forward, rub their eyes, and check the numbers again. This is one of those times. Somewhere many hundreds of light years away, a world floats around its star with the density of spun sugar. If you tried to place it in a giant bathtub of celestial imagination, it would seem almost eager to rise to the top. Not because it is hollow, not because it is fake, but because nature sometimes builds things that seem absurd until the measurements keep agreeing. Before we drift farther into this strange system, I would love to know where in the world you're listening from tonight, and what time it is in your corner of Earth right now. Perhaps it is late evening, and the streets outside are quiet. Perhaps dawn is beginning somewhere beyond your curtains. Perhaps you're tucked beneath blankets, while a distant radiator makes diplomatic negotiations with old pipes. Wherever you are, I'm glad you're here. And if you find this gentle voyage soothing, interesting, or simply a pleasant way to unwind after a long day, I'd be ever so grateful if you liked the video, subscribed, or shared this calm little corner with someone else who may need a slower moment. Now then, settle in, loosen the grip of the day, and let your thoughts become less urgent. Because tonight, we begin with a planet that looks less like a mighty giant and more like dessert. That alone would be enough to earn attention. But the real wonder of WASP-193b is not its nickname. It is what the nickname means. When astronomers say a planet is like cotton candy, they are speaking about density. Density is simply how much mass is packed into a given volume. A bowling ball and a beach ball can be similar in size, but one is dramatically more committed to gravity. The same idea applies to planets. Earth is dense. If you compressed all of Earth's mass into a sphere our current size, you would get exactly what you already have, which is a wonderfully practical arrangement. Jupiter, though made mostly of hydrogen and helium, is still dense enough overall because it contains an enormous amount of matter pulled tightly together by gravity. But WASP-193b seems to have taken a different path. It spreads a relatively small amount of mass across an enormous volume, creating a world that is physically huge, yet surprisingly insubstantial. Imagine constructing a cathedral out of mist. Imagine inflating a parade balloon until it rivals a building, then discovering it weighs less than expected by a ridiculous margin. That is the sort of puzzle astronomers adore. The story begins with the modern search for exoplanets, planets orbiting stars beyond our own sun. For most of human history, we could wonder about other worlds, write poems about them, argue philosophically about them, and dramatically point at the night sky. But we could not confirm them. Then technology improved. Telescopes became sharper. Detection methods became cleverer. Computers became patient enough to process oceans of data without demanding snacks every 7 minutes. And gradually, hidden planets began to reveal themselves. Some announced their presence by tugging gently on their stars, causing subtle wobbles. Others passed in front of their stars from our point of view, dimming the starlight by a tiny amount. This is called the transit method, and it has introduced us to thousands of worlds. Each transit is a small wink from the cosmos. A star shines steadily. Then, at regular intervals, it dips slightly. Something crossed in front of it. If that dimming repeats on schedule, there may be a planet there. From the depth of the dip, scientists can estimate the planet's size. From the star's wobble, they can estimate the planet's mass. Put those together and density emerges, and sometimes density says, you may want to sit down. That is how strange planets earn their reputations. Some are lava worlds hot enough to melt rock. Some are tidally locked, with one side in eternal day and the other in endless night. Some orbit two stars. Some are colder than old grudges. Then there are the super puffs. This informal category includes planets with very low densities and inflated sizes, often resembling gas giants that somehow forgot to bring enough material with them. WASP-193b belongs among these unusual company members, though it manages to stand out even there. And standing out among bizarre exoplanets is rather like winning a costume contest at a masquerade hosted by quantum mechanics. What makes such a world possible? At first glance, gravity should solve the problem. A planet of giant size ought to compress itself. Its own mass should pull inward, squeezing gas layers tighter and producing a denser structure. Yet some planets remain bloated, extended, and stubbornly puffed up. One likely reason is heat. Many of these worlds orbit very close to their stars. They receive intense radiation that heats their atmospheres, causing outer layers to expand. Picture a loaf of bread rising in an oven, except the loaf is planetary, the oven is stellar, and the recipe has not been approved by any sensible kitchen. Close orbits can also create tidal forces. Just as our moon tugs Earth's oceans, a nearby star can flex a planet's interior. That constant kneading may generate internal heat, further swelling the atmosphere. Then there may be composition. If a planet contains a relatively small core and a large envelope of light gases like hydrogen and helium, it can occupy tremendous space without carrying as much mass as expected. Still, even with these explanations, some planets remain difficult to model. Bull's WASP-193b appears to be one of those polite cosmic reminders that theories are works in progress, and that is healthy for science. Contrary to myth, scientists do not become upset when nature disagrees with expectations. Well, perhaps briefly, especially before coffee. But truly, surprises are valuable. They reveal gaps in understanding. They point toward better models. They remind us that the universe was under no obligation to consult our textbooks before forming itself. There is something charmingly humbling about that. We build equations, observe patterns, and grow confident. Then a cotton candy planet drifts by and rearranges the mood. Imagine what it might be like to approach such a world. From afar, you might see a giant sphere with pale atmospheric layers, perhaps hazy clouds high above deeper gas beneath. It could appear majestic and soft at once. As you descended, there would be no solid surface waiting politely below with a welcome mat. Gas giants do not usually offer that convenience. Instead, pressure would increase gradually, winds might rage, temperatures would rise, atmosphere would thicken into deeper and stranger states of matter. The idea of landing becomes less meaningful the farther down you go. It is less like arriving somewhere and more like entering an argument with physics. On a super puff world, the outer atmosphere may begin especially far from the denser interior. That means the visible radius can be huge even while much of the planet is tenuous gas. So in a sense, part of the size is atmosphere spread generously outward. If Earth had such habits, weather reports would need several additional departments. Yet while these planets sound whimsical, they are also fragile in a cosmic sense. A puffed atmosphere close to a star may slowly escape into space. Stellar radiation can strip lighter gases away over time. That means some superpuffs may be temporary phases in planetary life, swollen now, slimmer later. Even planets may experience eras they would rather not have photographed. This gives us another reason to pay attention. We may be seeing certain worlds during brief transitional periods. Catching them now is like opening a door at just the right moment. Astronomy often works this way. Because distances are vast and timescales immense, every observation is a snapshot. We do not watch most planets evolve in real time. We infer their stories from present clues: a planet's orbit, its mass, its radius, its star's age, its atmospheric chemistry, tiny signals gathered across darkness. From these fragments, scientists reconstruct histories, and sometimes the history says, giant, overheated, inflated, puzzling, ongoing. There is also a quieter emotional side to discoveries like this. Many of us grow up with a simple image of planets, rocky worlds like Earth, ringed giants like Saturn, icy outer bodies, neat categories lined up in educational posters. Those worlds are real and beautiful, but the wider galaxy is under no duty to remain tidy. Out there are planets raining molten glass sideways, worlds darker than coal, bodies denser than iron expectations, orbits so close to stars that years last days, and somewhere among them floats WASP-193b, asking us to expand our sense of what a planet can be. That may be the greatest gift of exoplanet science. Not merely more objects to catalogue, but a wider imagination. Each strange world loosens an assumption. Each measurement stretches the borders of normal. Each surprise teaches caution toward phrases like, "that could never happen." Because in astronomy, those phrases age badly. As you rest there now, perhaps with the room dim and your thoughts slowing, it is pleasant to remember that reality remains creative. Even after centuries of study, even after equations, observatories, spacecraft and simulations, the universe still has the ability to produce something that sounds invented. A cotton candy planet. Not in a fairy tale, not in a cartoon, in measured data. That does not make science less rigorous. It makes it more delightful. Soon, we will move deeper into how astronomers found this world, how they measured it, and why confirming something so airy requires great care. Because unusual claims must survive unusual scrutiny. For now, simply hold the image in mind. A star shining far away. A giant planet circling close. A world broader than giants we know, yet strangely light. A sphere of gas so expanded that it seems almost hesitant to be matter at all. Long before anyone knew that WASP-193b would earn comparisons to cotton candy, it was simply another faint possibility hidden in starlight. That is how many remarkable discoveries begin. Not with fireworks, not with dramatic alarms ringing through observatories, not with a scientist dropping a teacup in slow motion while whispering, "Good heavens!" Usually they begin with data, rows of numbers, tiny changes in brightness, repeated signals so subtle they would be invisible to the human eye, patterns buried inside noise, a star doing something just odd enough to deserve attention, and somewhere in that quiet process, this improbable world first raised its hand. To appreciate how extraordinary that is, it helps to remember that planets beyond our solar system are very difficult to see directly. Stars are bright, planets are dim. A star can outshine its planets by enormous factors, rather like trying to spot a firefly circling a lighthouse from several towns away. Even worse, these systems are far away, so astronomers often do not see exoplanets in the everyday sense. Instead, they detect what planets do. They tug on stars, they block small portions of starlight, they heat their surroundings, they leave fingerprints in spectra, they reveal themselves through influence rather than appearance. In a way, many planets are introduced to us through manners rather than faces. WASP-193b entered astronomy through one of the most successful techniques ever devised for finding distant worlds: the transit method. This method is elegant in its simplicity. If a planet's orbit happens to line up just right from our perspective on Earth, the planet passes in front of its star. As it does, it blocks a tiny fraction of the star's light. The star briefly dims. Then the brightness returns. If this happens again and again at regular intervals, that repeating dip may be caused by an orbiting planet. Imagine watching a distant porch light while a moth circles in front of it. You may never see the moth clearly, but you notice the flicker. astronomers do this with stars. Only instead of one porchlight, they monitor thousands or even millions of them, using telescopes on Earth and in space, patiently waiting for those tiny flickers. The project name attached to this world gives a clue to its origins. The WASP in WASP-193b stands for the Wide-Angle Search for Planets, a major survey designed specifically to hunt transiting exoplanets. Despite sounding like something that might interrupt a picnic, WASP was in fact a very productive scientific effort. The WASP program used arrays of cameras with wide fields of view, allowing astronomers to observe large portions of the sky repeatedly. Instead of staring deeply at one star, these instruments watched many stars at once, night after night, looking for regular brightness dips. It was less like examining one grain of sand with a microscope, and more like scanning an entire beach for footprints. This broad approach proved extremely effective. Many hot Jupiters and other large close-orbiting planets were found through such surveys. Giant planets are easier to detect through transits because they block more light, especially if they orbit close to their stars and transit often. A small, rocky world orbiting once every few years is shy and elusive. A giant world whipping around its star every few days is comparatively difficult to ignore. Somewhere in those survey observations, the star known as WASP-193 showed periodic dimming. At first, that does not automatically mean planet. Stars can be mischievous. They can have spots on their surfaces that rotate in and out of view, creating brightness changes. Binary stars can eclipse one another. Instrumental errors can imitate signals. Atmospheric effects from Earth-based observations can add noise. Computers, while useful, occasionally remain committed to chaos. So when astronomers notice a repeating transit-like signal, skepticism arrives immediately, carrying clipboards. The first glimpse is only the beginning. Researchers examine the period of the dips. Are they consistent? Is the depth stable? Does the shape resemble a planetary transit, with smooth ingress and egress as the object moves across the star's disk? Could it instead be two stars eclipsing each other in disguise? This stage of exoplanet discovery involves caution, statistics, and many plots with labels. For WASP-193b, the signal persisted. That meant something was repeatedly crossing the face of the star. Once a candidate survives initial scrutiny, astronomers seek follow-up observations. More telescopes join the effort. Better precision is requested. Nights are scheduled. Coffee is prepared in internationally significant quantities. Follow-up matters because survey instruments are designed to detect candidates, not always to characterize them fully. They cast wide nets. Confirmation requires finer tools. One key next step is measuring the star's radial velocity. This method tracks the tiny wobble of a star caused by an orbiting planet's gravity. Though the planet orbits the star, both bodies actually move around a shared center of mass. The star shifts slightly toward and away from us. That motion changes the starlight through this Doppler effect. Light shifts a little bluer when the star moves toward us, a little redder when it moves away. From this wobble, astronomers estimate the planet's mass. Now, something beautiful happens when transit data and radial velocity data are combined. Transit tells you size, wobble tells you mass plus size tells you density, and density tells stories. At first, those stories are often surprising. For a planet the size implied by the transit signal around WASP-193, astronomers expected something substantial. Large radius often suggests a gas giant with respectable mass. Instead, the measurements pointed elsewhere. The world appeared enormous in volume, but strangely light. That is the sort of result that does not immediately get framed and celebrated. It gets checked repeatedly. Because when numbers imply a planet of bizarrely low density, scientists ask the proper question: what did we miss? This is not pessimism, it is professionalism. Could the star's size be misestimated? If the star is larger or smaller than assumed, the planet's radius changes too. Could there be another hidden star contaminating the light? Could stellar activity mimic part of the signal? Could the radial velocity amplitude be difficult to measure because the planet's pull is so weak? Each possibility must be examined. The host star itself becomes important. To know the planet, you must know the star. Astronomers study stellar temperature, luminosity, composition, and radius. They compare models, they use spectra, they refine uncertainties. Stars are the rulers by which exoplanets are measured. A misread ruler gives odd furniture dimensions, so the star WASP-193 had to be understood carefully before confidence in the planet could grow. As data improved, the picture held. The planet was real, the transit was genuine, the mass remained low, the radius remained huge, and slowly the first glimpse transformed into recognition. This was one of the puffiest planets known. There is a quiet thrill in moments like that. Not because science enjoys confusion for its own sake, but because confusion often marks the edge of understanding. When results match expectations perfectly, knowledge is confirmed. When results do not, knowledge expands. Some astronomers likely felt delight mixed with practical inconvenience. Delight because strange worlds are exciting. Inconvenience because strange worlds require papers, explanations, additional analysis, and the emotional burden of many reviewer comments. Still, this is how the field advances. The transit method itself deserves a moment of admiration here. Think of what it asks us to do. Observe a star hundreds or thousands of light years away. Measure its brightness so precisely that a dimming of perhaps 1% or less becomes visible. Repeat observations over many orbits. Infer the existence of an unseen world. Estimate that world's size. Then combine separate measurements to estimate mass. Then conclude that the planet has the density of spun sugar, all while standing on a rotating planet beneath a turbulent atmosphere. Humanity can be impressive when motivated. The orbital period of WASP-193b also helped make it detectable. Close-in planets transit frequently. A planet orbiting every few days offers many chances to observe dips in starlight. A planet orbiting every 12 years is less cooperative and perhaps somewhat theatrical. Frequent transits mean faster confirmation and richer data sets. Yet close-in planets also bring complications. Their stars may be active, their atmospheres may be inflated, their systems can be dynamically interesting. Heat can distort assumptions based on cooler planets farther out. That seems especially relevant here. As astronomers pieced together the first reliable portrait of this world, it became clear they were not dealing with an ordinary giant planet. This was not simply another Jupiter cousin. It was something more delicate, more expanded, more puzzling. The nickname Cotton Candy Planet captures public imagination because it is vivid. But behind that nickname lies serious observational work. No one looked through a telescope and saw carnival confection orbiting a star. They saw dips in brightness, wobbles in spectra, model fits, error bars, repeated checks. Then they earned the right to say something whimsical. That is one of science's nicest habits. Playful conclusions built on disciplined methods. There is also something touching about how indirect all this is. We cannot stroll there. We cannot scoop a sample. We cannot deploy weather balloons with logos and cheerful slogans. We cannot yet send probes to most exoplanets. So we listen to light. We study timing. We infer. We let photons that travelled across space tell us what happened at their source. And if interpreted carefully enough, those photons can reveal a world that should barely hold itself together. Perhaps that is worth pausing over tonight. A distant star flickers by a tiny amount. On Earth, instruments record it. People compare notes, write code, argue kindly, revise assumptions, and eventually conclude that a giant low-density planet circles there. Knowledge arrives softly. No trumpet announces it, just better certainty. By the time the discovery entered public conversation, the dramatic part was already over. The patient part had happened first. Years of surveys, follow-up nights, calibration, statistical confidence, peer review, refinement. That often goes unseen, but it is the foundation of every headline that says, astronomers discover. In reality, astronomers usually discover something gradually, and so the first glimpse of WASP-193b was not one moment but many moments layered together. A small dip noticed, a candidate flagged, more observations gathered, mass estimated, density questioned, numbers rechecked, then acceptance. There really was a giant world there, astonishingly light for its size, circling close to its star as if this were perfectly normal behaviour. The universe often behaves with complete confidence while we scramble to understand it. By the time astronomers were confident that WASP-193b was real, a second realization quietly followed behind the first. This planet was not merely unusual, it was inconvenient. Now, inconvenient planets are some of the most valuable objects in astronomy. Ordinary worlds help confirm what we already understand. Strange ones expose where our understanding is incomplete. They force theories to stretch, revise themselves, and occasionally sit in a corner for reflection. WASP-193b belongs to that honoured category. Because once its size and mass were combined, the numbers implied something that seemed deeply unreasonable. A giant planet with density so low that it challenged standard expectations for how planets form, how atmospheres behave, and how gravity tends to run its affairs. It is one thing to discover a large planet. It is another to discover a large planet that appears to contain far less material than its dimensions suggest. Imagine arriving at a warehouse and learning it weighs less than a garden shed. You would have questions. Astronomers did too. To understand why this world seemed not to belong, we should begin with a basic planetary instinct. Bigger things usually need more stuff. That statement is not mathematically perfect in every circumstance, but it serves well enough for an evening stroll through exoplanet science. If a planet is enormous in radius, then maintaining that size generally requires either substantial mass, intense heating, unusual composition, or some combination of all three. Gravity pulls inward, pressure balances outward, matter compresses under weight. Gas giants do not simply puff forever like unattended balloons. At least that was the polite expectation. Yet WASP-193b arrived looking larger than Jupiter in radius, while carrying dramatically less mass than one might assume for such scale. That creates a puzzle because radius and mass are not independent trivia. Together they reveal internal structure. Take Earth. Its radius and mass indicate a rocky, metal-rich body with a dense interior. Take Jupiter. Its enormous mass and size reveal a giant planet made mostly of hydrogen and helium, compressed by gravity into deeper exotic states below. But take a planet with giant size and surprisingly low mass, and suddenly the usual categories become less comfortable. It is like opening a cookbook and finding a loaf of bread that occupies the whole oven, yet used almost no dough. Something unusual happened during preparation. In planetary science, one common framework for giant planets begins with core accretion. A solid core forms first from dust and ice in a young protoplanetary disk. Once that core becomes large enough, it rapidly gathers surrounding gas, building a thick atmosphere and growing into a gas giant. This model has explained much about worlds like Jupiter and Saturn, but for a world like WASP-193b, questions multiply. How massive was its core? How did it gather gas without becoming denser? How did it end up so expanded? How has it remained that way? And perhaps most pressing of all, why has it not shrunk into something more ordinary? Planets cool over time. Young giant planets can begin hot and inflated after formation. They radiate energy into space, contract gradually, and become more compact. This cooling and contraction process is a standard part of giant planet evolution. So if a mature planet still appears dramatically bloated, something may be supplying extra heat or delaying contraction. That is where close stellar orbits become suspects. Many superpuff planets orbit near their stars. WASP-193b does as well. Close proximity means intense irradiation. The star bathes the planet in energy. Outer atmospheric layers heat up and expand. That helps, but sometimes it does not help enough. Models can reproduce some inflation, yet the most extreme low-density planets often remain stubbornly difficult to explain fully. The atmosphere can be heated, yes. The gas can swell, yes. But reaching the observed size with such low mass may still strain assumptions. This is where astronomers become both excited and slightly haunted. Because whenever nature keeps matching measurements while resisting explanation, it suggests there is more to learn. One possibility involves atmospheric opacity. If the upper atmosphere traps heat efficiently, cooling slows. Imagine wrapping a hot loaf in too many towels. It stays warm longer, remains puffier longer, and is less eager to settle down. Another idea involves tidal heating. If a planet's orbit is slightly eccentric, not perfectly circular, the star's gravity can flex the planet repeatedly. Internal friction generates heat. The planet is kneaded by gravity itself, and that heat may contribute to expansion. This sounds dramatic because it is. Entire worlds warmed by being rhythmically squeezed. Still, another possibility is that some of these planets formed farther from their stars and later migrated inward. In colder outer regions, giant planets may gather gas differently. Then orbital interactions with the disk or neighbouring planets can move them closer to the star. Migration is common in exoplanet theory. Many hot Jupiters likely did not form where we see them now. So perhaps WASP-193b began elsewhere, then drifted inward and entered a new heated phase. That helps tell a story, but not always the whole story. There is also the matter of atmospheric escape. A low-density planet orbiting close to a star may gradually lose gas under stellar radiation. High-energy photons can heat upper layers enough that particles escape to space. Over immense timescales, this can reshape a planet. Yet here we meet another tension. If such worlds lose gas efficiently, how do they remain so bloated? If they retain gas efficiently, why are they so light to begin with? The universe has a talent for offering two awkward questions at once. Some scientists classify planets like this as superpuffs, a nickname both charming and scientifically provocative. These are planets with radii comparable to giant worlds, but density is closer to foam, mist, or baked goods that were not supervised properly. WASP-193b is among the most extreme examples, and extremes are where theories earn their keep. Consider what gravity should do over time. Gravity is the great organizer. It gathers clouds into stars, it rounds rubble into planets, it compresses interiors, it rewards seriousness. Yet here is a world where gravity seems to have accepted an unusual compromise. The planet remains extended, diffuse, airy. Not gravity-free, of course. Gravity still holds the atmosphere overall, but compared with denser giants, the grip appears gentle. If you could somehow hover in the upper atmosphere, you would not be standing on a solid surface. There may be none in the familiar sense. Instead, you would encounter layers of gas descending toward deeper pressures, hotter temperatures, and stranger states of matter. The visible size of such a planet may include very high atmospheric layers far above any compact interior. This matters because radius measurements from transits depend on where the atmosphere becomes opaque enough to block starlight. If haze or gas extends high, the planet appears larger. In other words, part of the bigness may be atmospheric presentation. Still, even allowing for that, the world remains extraordinary. There is something delightful about how this challenges our emotional assumptions too. We often imagine space as harsh, severe, metallic, unforgiving. And certainly much of it is. Vacuum is not known for softness. Yet then astronomy introduces a giant world likened to cotton candy. Not because it is sweet, not because it is pink, probably disappointing to carnival vendors everywhere, but because even in brutal cosmic conditions, matter can arrange itself into something unexpectedly delicate. That contrast makes the universe feel less repetitive. It also reminds us that our solar system, while beautiful, is only one sample. If we had known only our own planets forever, we might assume giant planets come in Jupiter and Saturn varieties, rocky planets in Earth and Mars varieties, icy bodies in Neptune-like forms, and so on. Then, exoplanets arrived and politely wrecked the furniture. Worlds denser than iron expectations, planets hugging stars in day-long years, gas giants larger than expected, mini-Neptunes we do not have here, and superpuffs like WASP-193b that seem assembled from overconfidence and warm air. This broadens not just science, but perspective. The phrase, "shouldn't exist," does not mean impossible under the laws of physics. It means difficult to reconcile with simplified expectations or current models. Nature has not broken rules. Rather, we may have mistaken our summaries for the rules themselves. That distinction is important. When scientists say something should not exist, they usually mean, we need better explanations. And that is one of the healthier sentences in knowledge. Perhaps somewhere tonight, as you listen in a quiet room, it is comforting to remember that confusion is not failure. It is often progress in disguise. Astronomy advances through mismatch. Prediction meets observation. Observation wins. Then prediction improves. WASP-193b participates beautifully in that tradition. Its very awkwardness makes it useful. Every new measurement of its mass, radius, atmosphere, temperature, and host star properties helps constrain models. Every telescope that studies it turns surprise into information. One day, planets like this may seem straightforward. Future students may read simple explanations and wonder why earlier astronomers were so troubled. This happens often in science. There was a time when the motions of planets themselves were perplexing. There was a time when stars were mysterious lights of uncertain nature. There was a time when galaxies beyond our own were debated. Today we discuss ultra-low density exoplanets over tea. Progress can be measured in increasingly specific astonishment. And still, some part of the charm remains in not knowing fully. There is a giant world far away, larger than reason first expects, lighter than intuition prefers, circling its star with complete composure. It does not care that we find it troublesome, it simply exists. There is a special kind of disbelief reserved for numbers that seem too strange to be true. Not dramatic disbelief, not the sort involving gasps, overturned furniture, or someone pointing wildly at a graph. Astronomy is usually calmer than that. It is more often the quiet disbelief of a researcher leaning closer to a screen, narrowing their eyes and saying, "Well, that cannot be right," then checking everything twice. That is the mood many unusual planets inspire, and WASP-193b is a fine example. Because calling a planet impossible is usually shorthand for something more precise. The measurements imply a world that resists expectation, and measurements are where all of this truly lives, not in nicknames, not in headlines, not in dramatic illustrations of giant pastel clouds floating through space. The real mystery begins with three simple ingredients: mass, size, and density. Those three numbers, or rather carefully estimated values with uncertainties attached, can tell astronomers astonishing things about a world they may never see directly. They can hint at whether a planet is rocky or gaseous, compact or bloated, young or evolved, ordinary or deeply inconvenient, and in the case of WASP-193b, they suggested something so airy that the universe seemed to be teasing us. Let us begin with size. For exoplanets, size is commonly estimated through the transit method. When a planet crosses in front of its star from our viewpoint, it blocks a tiny portion of the starlight. The star dims slightly. That dip in brightness can be measured. A larger planet blocks more light. A smaller planet blocks less. This relationship is elegantly simple, though reality adds paperwork. If you know the star's size, then the fraction of light blocked reveals the planet's radius. That means a planetary measurement depends heavily on stellar knowledge. If you misjudge the star, you misjudge the planet. Stars are generous enough to shine, but they rarely hand us neat labels reading exact radius included. So astronomers must study the host star carefully. Temperature, luminosity, spectra, composition, age estimates, stellar models, distance measurements. All of these help refine the star's properties, which then sharpen the planetary ones. In the case of WASP-193, researchers needed to know the star well enough to trust the transit signal. Once they did, the planet's radius emerged as enormous. Roughly speaking, WASP-193b appeared comparable in size to giant planets like Jupiter, even somewhat larger in radius. That alone would not be shocking. Large planets exist. The galaxy is not short on oversized personalities. But then came the mass. Mass is harder. You cannot simply watch a star dim and know how heavy the planet is. A beach umbrella passing in front of a lighthouse tells you width, not weight. To estimate mass, astronomers often use radial velocity measurements. As a planet orbits, its gravity tugs on the star. The star moves slightly in response, wobbling toward and away from us. That motion shifts the star's light through the Doppler effect. When the star moves toward us, wavelengths shorten a little. When it moves away, they lengthen a little. By tracking these tiny shifts, scientists estimate how strongly the planet pulls on the star. That reveals mass. At least it reveals a minimum mass directly, with geometry and orbital information helping refine the rest. This process requires exquisite precision. The motions involved can be tiny. We are speaking of detecting stellar movement caused by an unseen companion across vast distances. It's like noticing a grand ship rock slightly because a cat walked across the deck. And yet humanity built instruments capable of doing exactly that sort of thing, which remains impressive. When the wobble data for WASP-193b were combined with transit data, the planet's mass came out surprisingly low for something so large. Now the stage was set. Because once radius and mass meet each other, density enters. Density is simply mass divided by volume. Volume grows quickly with radius. Increase the size of a sphere and volume expands dramatically. So a planet can become much larger in volume without proportionally increasing in mass. Still, there are limits set by structure, gravity, temperature, and material behavior. This is why density is so revealing. A dense planet may be rocky or metallic. A moderate density giant planet may be gas-rich but gravitationally compressed. A very low density planet suggests extensive light gases, inflated atmosphere, weak overall compactness, or all three. And WASP-193b landed in the extreme low density category. So low in fact that comparisons to cotton candy became irresistible. It is worth noting that such comparisons are metaphorical, not culinary. No telescope has reported caramelized weather systems or fairground music in orbit. The nickname simply captures how little material seems packed into such a large space. Imagine a sphere broader than Jupiter, yet composed with far less heft than the intuition expects. That is the puzzle in numerical form. Now, when astronomers get startling density results, they do not immediately announce that physics has retired. They inspect the uncertainties. Every measurement comes with error bars, ranges of plausible values based on instrument precision and modelling limits. Good science is not merely numbers, it is numbers with honesty attached. Could the radius be overestimated? Could the star be larger or smaller than believed? Could another hidden star contaminate the light, making the transit seem deeper? Could the radial velocity signal be weak or noisy? Could stellar activity imitate motion? Could orbital assumptions need revision? Each of these questions matters. In exoplanet work, tiny shifts in stellar parameters can change planetary conclusions substantially. A slightly different stellar radius alters planetary radius. A different stellar mass can affect orbital interpretations and derived quantities. This is why unusual planets often receive follow-up observations from multiple teams and instruments. Strange claims deserve patient scrutiny. And in this case, the strange conclusion persisted. The data continued to support a world of giant radius and low mass. There is something almost theatrical about density, because it transforms familiar words. Large no longer means heavy. Giant no longer means massive. Planet no longer means something easy to picture. The numbers quietly rearrange intuition. Let us compare with familiar examples. Earth is compact and dense, built of rock and metal. Saturn is famously low in average density compared with rocky worlds, owing to its hydrogen-helium composition. It's often said that Saturn would float in a sufficiently large ocean if one could be found, and if we overlooked several engineering details. Even Saturn, however, has company now in the contest for airy grandeur. Planets like WASP-193b push low density to more dramatic territory. They belong to a broader group nicknamed superpuffs, worlds whose radii are surprisingly large relative to their masses. This leads to a subtle but important point. When astronomers report a planet's radius, that radius often corresponds to the altitude where the atmosphere becomes opaque enough during transit to block starlight effectively. In other words, the visible edge of the planet in transit may be high in the atmosphere. If a world has a swollen, extended atmosphere, the measured radius can be impressively large even though deeper layers hold more of the mass. So part of the planet's size may be atmosphere stretched far outward. That does not make the measurement wrong, it makes the object interesting. You are measuring the real extent at which the planet interacts with starlight, but it means exoplanet size can involve atmospheric architecture, not just compact bulk. For WASP-193b, that architecture appears dramatic. Its upper layers may be puffed by stellar heating. Its gravity may be comparatively weak at those heights. Its gas envelope may remain extended in ways that denser giants suppress more effectively. This is where numbers become physical stories. Mass tells you how much matter is there. Radius tells you how spread out it is. Density tells you whether gravity has gathered that matter tightly or allowed it to lounge expansively. And this world appears committed to lounging. There is another challenge hidden inside low-mass measurements. A planet that pulls weakly on its star produces a smaller radial velocity signal. That makes precision harder. The very thing making the planet interesting also makes it trickier to weigh. Some planets cooperate by being massive and obvious. Others whisper. WASP-193b seems to have chosen the whispering route while dressing dramatically. This combination of modest tug and giant transit silhouette is scientifically delightful. It also shows why exoplanet astronomy depends on multiple methods. No single measurement tells the whole story. Transit alone gives size but not weight. Wobble alone gives weight clues but not full radius. Together they reveal density, and density opens the door to composition and structure. This layered approach resembles solving a mystery from shadows, footsteps, and echoes. You never meet the suspect directly, yet eventually you know quite a lot. Perhaps tonight there is comfort in that. Across hundreds or thousands of light years, through noise, weather, hardware limits, and cosmic indifference, people can infer the properties of a distant world by reading tiny changes in light. That is a gentle kind of triumph. No conquest, no flag planted, just understanding, patiently assembled. And what understanding says here is simple and astonishing. There exists a giant planet whose mass is unexpectedly small for its breadth. Its density is among the lowest known. Its atmosphere may be greatly inflated. Its very measurements ask deeper questions about heat, formation, and survival. When astronomers describe a planet as fluffy, they are not suggesting softness in the everyday sense. No one is proposing pillows in orbit. There are no cosmic cushions, no atmospheric marshmallows, no giant celestial teddy bear drifting politely around a distant star. Space remains space, which is to say cold in many places, violent in others, and generally uninterested in comfort. And yet, in the language of planetary science, fluffy has become a useful word. Because sometimes technical accuracy needs a little help from imagination. When scientists call WASP-193b fluffy, they mean that for its enormous size, it contains surprisingly little mass. Its material is spread out over a vast volume. The average density is extremely low. Matter is present, certainly, but it is arranged in a way that makes the planet puffed, expanded, and unusually diffuse compared with more compact worlds. So fluffy in space means not soft to the touch, but sparse for the scale. It means a planet that occupies a great deal of room while weighing far less than expected. It means gravity has not packed the contents tightly. It means the atmosphere extends far outward. It means a giant world that seems, in some respects, more like foam than stone. That alone is enough to stretch intuition. On Earth, we are surrounded by dense things. Chairs are dense enough to trust. Floors are dense enough to appreciate. Bread is dense enough to discuss. Even clouds, which look airy, are composed of countless droplets and float within a thick atmosphere beneath them. But planets, in our everyday imagination, tend to be solid, or at least substantial. We picture mountains, crusts, oceans, iron cores, crushing pressure, enormous weight. Even gas giants like Jupiter feel mighty and compact in the mind. Their clouds may be gaseous, but their presence feels serious. Then astronomy introduces a world like WASP-193b, and seriousness becomes more nuanced. To understand this properly, it helps to separate two ideas that often get mixed together: density and gravity. Low density does not mean no gravity. A large low-density planet can still have significant gravity, because total mass matters. What changes is how that mass is distributed. If the material is spread across a larger radius, surface or atmospheric gravity at certain heights may be weaker than on our more compact object of similar mass. So fluffy does not mean weightless. It means extended. It means less tightly gathered. It means the planet's matter is occupying more space than expected. Imagine two suitcases with identical outer dimensions. One is packed by a meticulous traveller using compression cubes and concerning levels of determination. The other contains 3 shirts, a scarf, and optimism. Same size, very different density. Planets can be like that, though with more hydrogen. For giant exoplanets, the most common light materials are hydrogen and helium. These are the simplest and lightest abundant elements in the universe. Stars are mostly made of them. Gas giants contain large amounts of them. Under enough pressure, these gases behave in strange and fascinating ways. But if heating, weak gravity, and atmospheric structure allow hydrogen-helium envelopes to remain expanded, the planet can become very large without becoming proportionally massive. That is one route to fluffiness. WASP-193b likely contains a substantial gaseous envelope, but one that has swollen outward dramatically. Its close orbit around its star probably plays an important role. Intense radiation can heat upper atmospheric layers, causing them to expand. The hotter the gas, the more energetically particles move, and the more the atmosphere resists compactness. In simpler terms, the star may be helping inflate the planet. This is not unlike leaving bread dough somewhere warm and discovering it has become more ambitious than expected. There are limits to this analogy, mostly involving yeast. Still, stellar heating matters enormously. Many low-density exoplanets orbit close to their stars. These worlds receive energy far beyond what outer planets in our solar system experience. The result can be bloated atmospheres stretching to great heights. And when a planet transits its star, astronomers measure the radius at the altitude where the atmosphere blocks starlight effectively. If the upper atmosphere extends high, the planet appears larger. So fluffiness is not merely about interior composition, it is also about atmospheric reach. A planet may wear an enormous outer coat. This leads to an important point. Average density is an average. If you took the total mass and divided by total volume, you get one number. But the planet itself is layered. The outer atmosphere may be extremely thin and diffuse. Deeper down, pressure increases, gas becomes denser. Farther inward still, there may be a compact core or deeper compressed layers. So a fluffy planet is not uniform cotton candy all the way through. It is more like a world with vast airy outer regions above increasingly serious interiors. That distinction matters, because otherwise one might imagine bouncing gently into the atmosphere like a child into confectionery clouds. Reality would be less accommodating. Suppose somehow you approached WASP-193b in a fantastically advanced spacecraft, equipped with good insurance and emotional resilience. At first, you would encounter upper atmospheric layers. These could be thin, hot, and extended over enormous distances. The sky might be hazy, winds could be fierce, clouds may contain unfamiliar chemistry depending on temperature and composition. As you descended, pressure would rise, then rise again, then continue rising with professional dedication. Temperatures would likely increase as well. Deeper layers of gas become denser and more hostile. The concept of landing becomes increasingly theoretical. So fluffy does not mean safe. It means the path downward is long. Another useful comparison is with familiar low-density objects on Earth. Consider foam, sponge, whipped cream, or cotton candy itself. These seem light because much of their volume is empty space or gas trapped within structure. The solid material occupies only a fraction of the total volume. Planets are not literal foams in this sense, but the analogy helps explain why large size need not equal great density. A lot of room can contain surprisingly little substance. Now, why do astronomers care so much about fluffiness? Because density is a clue to history. Every planet is the result of formation conditions, composition, orbital evolution, heating, cooling, collisions, atmospheric escape, and time. Density summarizes many of those influences at once. A dense rocky world may have lost gas early, or formed inside the snowline where lighter volatiles were scarce. A gas giant of moderate density may have formed a large core and accreted massive envelopes. A superpuff like WASP-193b suggests a very different path, or a combination of processes still being studied. Perhaps it formed with a modest core and large envelope. Perhaps it migrated inward and became heated. Perhaps atmospheric opacity slowed cooling. Perhaps tidal heating added energy. Perhaps multiple effects cooperated like suspiciously organized accomplices. Fluffy planets force models to explain how giant atmospheres remain so extended over time. There is also the issue of survival. A low-density planet close to a star may be vulnerable to atmospheric escape. High-energy radiation can heat upper layers until gas streams away into space. Over long timescales, such a world might lose substantial material. So if we see a fluffy planet now, we may be catching it in a temporary state. Perhaps it was even puffier in the past. Perhaps it is slowly slimming under stellar pressure. Even planets, it seems, are not free from external expectations. This possibility makes such worlds especially interesting. They may represent evolutionary snapshots rather than permanent categories. Astronomy often works through snapshots. We do not usually watch a planet age in real time. We infer youth, maturity, erosion, inflation, migration, and change from present observations. A fluffy planet may be a clue to what many worlds pass through briefly. There is something pleasant about that thought. Even distant giants can have phases. The word fluffy also helps communicate science to the public. Technical phrases like extremely low bulk density inflated irradiated gas giant are accurate but perhaps less soothing before bed. Fluffy planet arrives with instant intuition. You hear it and understand something essential. Big, light, odd. That is useful communication. Science needs precision, yes, but it also benefits from metaphors that invite curiosity rather than intimidation. And once curiosity arrives, deeper understanding can follow. For instance, A fluffy planet can teach us that size alone misleads. On Earth, bigger animals tend to weigh more. Bigger buildings require more materials. Bigger boxes invite regrettable storage habits. But in planetary science, size must always be paired with mass. A planet larger than Jupiter may weigh less than expected. A planet smaller than Earth may be denser than iron-rich assumptions. Radius without mass is appearance. Mass without radius is mystery. Together they reveal character. WASP-193b has quite a character. It also reminds us that our solar system is only one local example. We grew up with planets like Mercury, Earth, Neptune and Jupiter. Beautiful worlds, but not a complete catalogue of possibility. Elsewhere, nature experiments more broadly. There are planets hotter than some stars' surfaces, planets with years shorter than weekends, planets circling dead stars, planets with densities so low they sound fictional. And somewhere among them, WASP-193b drifts in warm starlight, wearing an atmosphere far larger than modesty would advise. Perhaps the most human response to such a world is laughter, followed by wonder. Laughter because cotton candy planet sounds absurd. Wonder because it is real, measured through transits, weighed through stellar motion, discussed in serious journals by serious people who, one hopes, occasionally smiled while typing the phrase. Tonight, as the room grows quieter and your thoughts soften around the edges, it may be comforting to remember that reality is not limited by our first guesses. Sometimes the universe makes compact rocky worlds. Sometimes it makes elegant ringed giants. Sometimes it makes planets so airy that scientists reach for carnival metaphors. When people first hear that WASP-193b is as large as a giant planet, yet astonishingly light for its size, a natural question follows almost immediately. What is it made of? It is a sensible question. We ask it about nearly everything. Tables, clouds, mountains, soup, relationships, old batteries in drawers. Human beings like composition. We feel calmer when things can be broken into ingredients. So when a planet appears to be made of almost nothing, it sounds like a riddle, a scam, or a late-night advertisement for premium emptiness. But in planetary science, almost nothing does not mean literal nothing. Nothing is surprisingly difficult to package. Instead, it means matter with very low average density, spread across enormous volume, often dominated by the lightest elements in the universe, and that brings us to hydrogen. If the cosmos had a basic building material aisle, hydrogen would occupy far too much shelf space. It is the most abundant element in the universe by a comfortable margin. One proton, one electron, elegantly simple, relentlessly common. Stars are mostly hydrogen. Giant planets contain vast amounts of it. Nebulae glow with it. Entire chapters of cosmic history are written in hydrogen. Helium follows closely behind. 2 protons, usually 2 neutrons, 2 electrons. Calm, light, chemically reserved. Helium does not form dramatic bonds or unnecessary entanglements. It mostly minds its own business while making balloons seem more optimistic. Together, hydrogen and helium are the likely principal ingredients of worlds like WASP-193b. That means when we say this planet is made of almost nothing, we are really saying it is made largely of gases so light that, when expanded across a huge radius, the total density becomes extraordinarily low. There is still plenty of matter there, just not packed tightly. Imagine a cathedral built from mist. Imagine a stadium full of soap bubbles, each bubble replaced by hot hydrogen under gravity. Imagine an enormous blanket stuffed with very little filling. These analogies are imperfect, but they point in the right direction. Vast size does not always require vast heaviness. Now, giant planets are not simply balls of ordinary gas in the everyday sense. The deeper one goes, the stranger matter becomes. In upper atmospheric layers, hydrogen and helium may behave much as gases do elsewhere. Particles moving freely. Pressure relatively low. temperatures depending on altitude and stellar heating. Descend farther, and pressure rises dramatically. Gas compresses. Temperatures climb. Molecules may break apart. Exotic states emerge. In giants like Jupiter, deep hydrogen may become metallic hydrogen, a phase in which it conducts electricity like a metal under immense pressure. That is a sentence no one would have guessed from looking at a weather balloon. For WASP-193b, the internal story is likely similar in broad outline but different in degree. Because the overall density is so low, its outer layers may extend much farther before pressure climbs into more compact interior regimes. There may still be a denser deep region. There may still be a core. But the outer envelope seems greatly expanded. So this is not a hollow shell surrounding emptiness. It is a gradient world, diffuse above, denser below. Planetary interiors often resist tidy boundaries. Earth gives us crust, mantle, core. We like this. It is orderly. It sounds like a recipe. Gas giants are more subtle. Their layers blend. Pressure changes continuously. Composition may shift gradually. What counts as surface becomes philosophical. On WASP-193b, that philosophical problem becomes especially enthusiastic. Where does the planet begin? At the altitude where gases first become bound? At the level where atmosphere blocks starlight during transit? At the point pressure reaches 1 bar, like a familiar reference level? At the place your spacecraft begins regretting its life choices? Different definitions serve different purposes. This matters because the enormous radius of a super-puff planet often includes high atmospheric layers. In transit observations, the measured size corresponds to the altitude where the atmosphere becomes opaque enough to dim the star's light. If haze, gas, or clouds extend high, the planet appears larger. So part of what the planet is made of may be a vast outer envelope that is thin by earthly standards but still optically important. That is a remarkable concept. A world can look huge partly because of the reach of its atmosphere. It wears volume like a cape. Now let us talk about cores. Many formation models for giant planets begin with a solid core made from rock, metal, and ices gathered in a young protoplanetary disk. Once the core becomes sufficiently massive, it can attract large amounts of surrounding hydrogen and helium gas. That means even a fluffy giant may hide something compact at heart. A rocky or icy core, perhaps several Earth masses in size. We do not know every detail of WASP-193b's interior with certainty, because exoplanets rarely offer guided tours. But models often explore combinations of core size, envelope mass, temperature, and atmospheric structure to explain the observed radius and mass. Some solutions may involve a modest core and a very extended gaseous envelope. Others may allow heavier elements mixed through the interior. Still others depend strongly on heat. Which brings us to another ingredient: energy. A planet is not only made of matter. In a practical sense, it is shaped by heat content. Hot gas occupies more volume than cooler gas under similar conditions. If a close star constantly warms a planet's atmosphere, or tidal forces generate internal heating, the planet can remain inflated. So one could jokingly say, WASP-193b is made of hydrogen, helium, and a great deal of attitude. There is scientific truth hiding in that joke. Thermal energy helps support expansion. Without enough cooling, contraction slows. A young giant planet often begins large and hot. Over time, it radiates energy away and shrinks. But intense stellar irradiation may interfere with that process, especially for close-in worlds. Thus, composition alone does not explain fluffiness. Temperature matters deeply. There is also the possibility of clouds and hazes. Many exoplanet atmospheres likely contain particles formed from chemistry under exotic temperatures. Silicates, sulfides, hydrocarbon hazes, metallic vapors, and compounds that sound like laboratory disputes. These particles can affect how light passes through the atmosphere. A hazy upper atmosphere can increase the apparent radius in transit measurements. It can also hide deeper layers from observation. so in some sense the planet may be wrapped in a veil. This is one reason atmospheric spectroscopy is so valuable. By studying how starlight filters through the atmosphere during transit, astronomers can infer molecules present above. Water vapour, sodium, potassium, methane, carbon-bearing compounds and more may leave signatures depending on conditions and instrument sensitivity. For a planet like WASP-193b, such future observations may help reveal whether the outer envelope is clear, cloudy, escaping, chemically rich, or gloriously complicated. Now, let us pause on the phrase, almost nothing. Human intuition is built in dense environments. We live beneath a thick atmosphere but notice mostly solids. We handle wood, metal, stone, food, clothing, doors, cups, taxes. Our world trains us to think substance means firmness. But most of the visible universe is not solid in that way. Stars are plasma, nebulae are gas. Interstellar space, though thin, contains matter. Galaxies are structured by dark matter we infer but do not directly see. Even atoms are mostly empty space by scale. The universe is remarkably comfortable with low-density arrangements, so perhaps a fluffy planet is not unnatural at all. Perhaps it merely offends human furniture-based expectations. That thought has charm. We are the dense ones judging a diffuse cosmos. If you could somehow sample a cubic meter of upper atmosphere from WASP-193b, it might contain far less mass than you emotionally hoped. Yet multiply that by planetary scale, stack layers upon layers, and suddenly an enormous world emerges. Small densities over giant volumes still add up. This is one of the quiet lessons of astronomy. Scale changes everything. A teaspoon of neutron star matter would be absurdly heavy. A planet-sized sphere of hot hydrogen can be surprisingly light. Context is king. There is also fragility in such composition. Extended hydrogen atmospheres near hot stars may gradually leak into space. Ultraviolet radiation can heat upper layers until gas escapes. Some exoplanets trail atmospheric tails like comets. Others may be slowly stripped over eons. So if WASP-193b is made mostly of light gases spread thinly, it may not keep the same appearance forever. It could evolve, shrink, lose envelope mass, change category entirely. That means we may be seeing not just an odd object, but a moment in a long biography. Astronomy often grants us snapshots, not full documentaries, and what a snapshot this is. A distant star, a swollen giant world, a body whose bulk may be dominated by hydrogen and helium, heated and stretched into improbable dimensions. A planet whose stuff is common, yet whose arrangement is rare enough to puzzle experts. That combination happens often in nature. Familiar ingredients, surprising outcomes. Sand becomes glass, carbon becomes diamond, hydrogen becomes stars, hydrogen and helium, under the right circumstances, become something like WASP-193b. As the night grows quieter around you, there may be comfort in knowing that strange things do not always require strange ingredients. Sometimes the universe uses ordinary materials creatively. Sometimes almost nothing becomes something enormous. If this world is built from such light substances, how does it hold on to them at all? Why doesn't the atmosphere simply drift away into space under stellar heat and weak gravity? When we think about planets, gravity usually arrives in the conversation as the reliable adult in the room. Gravity builds stars, gathers dust into worlds, rounds rough objects into spheres, keeps moons in orbit, keeps atmospheres attached, and prevents oceans from wandering off into philosophical independence. It is patient, persistent, and rarely dramatic about its accomplishments. So when astronomers encounter a planet like WASP-193b, one of the first questions becomes almost immediate. How is gravity handling this situation? Because here we have a world with giant size, unusually low density, and a swollen atmosphere close to its star. Those facts together imply something important. At the outer layers, gravity may be comparatively gentle, not absent, not meaningless. but gentler than one might expect from a planet of such impressive dimensions. That distinction matters. Many people instinctively connect size with strong gravity. If something is huge, it must pull hard. That feels sensible. Yet gravity at a planet's cloud tops or atmospheric boundary depends on both total mass and radius. The larger the radius, the farther you are from the centre of mass, and gravity weakens with distance, so a planet can be visually enormous while exerting more modest surface or upper atmosphere gravity than intuition suggests. This is one reason WASP-193b fascinates astronomers. It appears broad and grand, but much of that grandeur may come from extended atmospheric layers rather than tightly packed bulk. Imagine two hills. One is steep, compact, and made of rock. The other is wide, soft-edged, and spread gently across a landscape. From a distance, the second may look larger, but climbing it can feel less severe. Planetary gravity sometimes works like that. A compact, massive world can grip fiercely. An inflated, low-density world may reach farther while holding more softly. To discuss this properly, we should distinguish between average gravity and local gravity. Deep inside any giant planet, gravity can become complicated. As mass accumulates beneath you, pull changes with depth and structure. But for exoplanets, when people casually discuss gravity, they usually mean the acceleration near the measured radius or atmospheric level relevant to observations. And for a super-puff planet, that level may sit high in a greatly expanded atmosphere. So when we say gravity is weak, we often mean weak at the outer boundary where the planet presents itself. That is rather poetic in a practical way. A planet can look mighty at the edge while being gentle there. Now, why does this matter so much? Because atmospheres are held by gravity. Gas particles move constantly. The hotter they are, the faster they move. If enough particles in the upper atmosphere move fast enough to escape the planet's gravitational pull, the atmosphere can gradually leak into space. This process is called atmospheric escape, and it is one of the great long-term sculptors of planets. On small worlds with weak gravity, light gases like hydrogen are hard to keep. That is one reason Earth has little free hydrogen atmosphere today compared with giant planets. Earth's gravity is respectable, but hydrogen is especially nimble. On massive compact giants, gravity grips more strongly, helping retain enormous gaseous envelopes. But on an inflated, low-density world close to a hot star, conditions become more delicate. The star heats the atmosphere, the gas expands, the outer layers sit farther from the centre, gravity weakens there, escape becomes easier. You can see why astronomers start asking pointed questions. How has WASP-193b managed to remain so puffed up? Why has it not shed more atmosphere already? Are we seeing it during a temporary phase? Has the star been gentler than feared? Is the planet more massive than first assumed within uncertainties? Or is planetary survival more flexible than our models once believed? All excellent bedtime questions. There are several ways a world like this may keep hold of itself. First, even weak planetary gravity on a giant world can still be substantial compared with human experience. Weak relative to Jupiter does not mean weak relative to a person dropping their keys. Second, atmospheric escape can be slow on human timescales. A planet may lose gas steadily over millions or billions of years and still appear robust during the brief moment we happen to observe it. Third, not all gas escapes equally. Temperature structure, magnetic effects, composition, stellar activity, and atmospheric chemistry all influence how efficiently material is lost. So the phrase barely holds on is more dramatic than literal, though not entirely unfair. This may be a world balancing in a delicate regime where heating tries to loosen the atmosphere while gravity works constantly to keep it bound. There is something elegant in that tension. The star pulls and heats, the planet swells, gravity resists, gas drifts upward, physics negotiates continuously. If planets had internal dialogue, this one might sound tired. Let us imagine approaching WASP-193b in an impossibly capable research craft. At first, you encounter the high atmosphere, perhaps tenuous, hot, and extended over vast distances. The pull downward may feel milder than expected for a giant world. You are far from the centre, after all, hovering near the outer fringe of a swollen envelope. Descend deeper, and gravity may strengthen somewhat depending on the internal mass distribution. Pressure certainly rises, winds may intensify, temperatures increase, the environment becomes less whimsical and more persuasive. This is a common trick in astronomy. Objects that sound playful from afar become serious up close. There is no cotton candy softness waiting there, only gas, heat, pressure, and scale. Still, the low outer gravity has major consequences. It affects atmospheric thickness, it influences escape rates, it shapes how starlight filters through the planet during transit. It may help explain why the measured radius is so large. A more weakly bound atmosphere can extend higher before compressing into denser layers. That means the visible edge of the planet may lie very far out. Once again, the planet wears volume generously. There is another force in the story too, the gravity of the host star. Close-in exoplanets like WASP-193b orbit near their stars, which means stellar gravity exerts powerful tidal influence. The star's pull is stronger on the near side than the far side of the planet, stretching the world slightly. These tidal effects can distort atmospheres, and in some cases help gas escape through regions where the planet's grip is weakest. You might picture the planet as holding a great cloak of gas while the star steadily tugs at one sleeve. Over time, some fabric may slip free. This leads to the concept of the Roche lobe, the region around a planet within which material remains gravitationally bound primarily to that planet rather than the star. If an atmosphere swells near or beyond this boundary, escape can become more efficient. For some extreme worlds, atmospheres may overflow like steam from a pot. Whether WASP-193b approaches such conditions in detail depends on exact parameters, but the general principle matters. Close stars complicate gravity. Planets do not keep their atmospheres in isolation. They keep them while being heated and tugged by nearby suns. This is why exoplanet science is so rich. Every quantity connects to others. Mass influences gravity. Gravity shapes atmosphere. Atmosphere changes radius. Radius alters density. Stellar heat affects escape. Escape changes future mass. One strange number often has several causes, and one soft-looking planet may embody an entire chain of interacting processes. There is something deeply human in how we respond to gravity too. We often think of strength as firmness, heaviness, forcefulness. Yet in nature, balance can matter more than brute force. WASP-193b may persist, not because gravity dominates absolutely, but because it dominates enough to remain a planet, enough to hold most of its gas for now, enough to maintain identity while change slowly unfolds. Enough can be powerful. Perhaps that is a comforting phrase for more than astronomy. Another curiosity arises when we compare such worlds with our own solar system. Jupiter possesses immense gravity and a compressed deep interior. Its atmosphere is thick, but its overall density and mass give it a firmer hold on gas. Saturn is less dense overall, yet still substantial and stable in the cooler outer solar system. Move a Saturn-like world very close to a star, heat it strongly, and new behaviours emerge. Move an already low-density giant inward, and you may get something like a super puff. Location matters. The same ingredients placed in a different oven produce a different cake. Astronomy repeatedly teaches this. Now consider timescales. If this planet is gradually losing atmosphere, the process may unfold over hundreds of millions or billions of years. Entire civilizations could rise, debate taxes, invent umbrellas, and vanish while the planet merely loses a modest outer fraction of gas. Cosmic change is often patient. So when we say it barely holds on, We are describing a long negotiation, not an immediate collapse. Tonight, somewhere beyond ordinary sight, a distant star shines on a giant world whose atmosphere may sit lightly in its gravitational hands, not falling apart, not entirely secure, simply existing in a delicate middle ground. That may be one of the most common conditions in the universe. Not perfect stability, not instant ruin. Sustained balance under pressure. Far from being a lonely object drifting through darkness, WASP-193b lives in constant conversation with its star. That conversation is not verbal, of course. Stars are poor listeners and even worse at taking turns. Instead, they communicate through gravity, radiation, magnetic influence, tidal forces, and relentless streams of energy crossing space every second. For many planets, a star is simply the centre of the system, the anchor around which all paths curve. For this world, the star is much more than that. It is architect, furnace, disciplinarian, and perhaps the main reason the planet looks so strange at all. Whenever astronomers discover an unusual planet, one of the first questions is not only, what is the planet like, but also, what sort of star is it living beside? That question matters because planets are shaped by their neighbourhoods. A rocky world near a hot star may become scorched and barren. An icy body far away may remain frozen and dim. A giant planet in a mild outer orbit may cool gradually over billions of years. But a swollen low-density world circling close to a sun-like star enters a far more dramatic arrangement. And that appears to be the case for WASP-193b. Its host star, WASP-193, is broadly similar to our own Sun in general type. Though stars always keep their own personalities through differences in size, age, temperature, composition and activity, even small differences matter. A slightly hotter star emits more energetic radiation. A younger active star may flare more often. A more evolved star may brighten over time. These changes can strongly affect close planets, and close is the key word here. Many exoplanets discovered by transit surveys orbit astonishingly near their stars. Some complete an orbit in only a few days. Compared with the leisurely paths of planets in our solar system, these are lives lived at speed. Mercury, our innermost planet, circles the Sun in about 88 Earth days. That once seemed brisk enough. Then exoplanet astronomy arrived and politely laughed. Hot Jupiters, ultra-short period planets, scorched mini-Neptunes, and inflated giants have shown us worlds that race around their stars with astonishing haste. WASP-193b belongs to that fast-living category. Its orbit places it near enough to its star that the relationship is not subtle. At such distances, sunlight is no gentle background glow. It is a dominating force. The planet receives intense stellar energy. Day after day, orbit after orbit, radiation pours into its atmosphere. Gases heat, layers expand, winds likely surge, chemistry changes. Structures that might remain compact farther out can become swollen here. This is one of the leading reasons the planet appears so inflated. The star may be puffing it up. There is something almost comic in that phrase, but scientifically it carries real weight. Atmospheric heating is serious business. Gas responds strongly to temperature. Warm it, and it tends to expand. Keep warming it, and upper layers can become extended over enormous distances. On a planet already rich in light gases like hydrogen and helium, this effect can become dramatic. That means the giant measured radius of WASP-193b may owe much to the star's constant influence. Without that nearby furnace, the planet might be smaller, denser, and less famous. Some stars create celebrities. There is also tidal locking to consider. Many close-in planets become tidally locked over time. This means one side of the planet continually faces the star while the other faces away, much as our moon always shows the same face to Earth. If WASP-193b is tidally locked, one hemisphere may live under perpetual daylight while the other remains in endless night. Imagine that weather forecast. One side permanently heated, one side permanently dark. Between them, a twilight boundary where winds may roar as atmosphere redistributes heat across the globe. Such planets can experience fierce circulation patterns. Gas heated on the day side rises and moves toward cooler regions. Jet streams may wrap around the world. Temperature contrast can be extreme or partially smooth depending on atmospheric depth and wind efficiency. For a fluffy giant with extended atmosphere, these flows may be especially complex. No gentle breeze likely exists there. Only global scale arguments between hot gas and cooler gas. Gravity is not the only force tying star and planet together. Tides matter too. Just as the moon raises tides in Earth's oceans, a nearby star can raise tides within a planet itself. On a gaseous world, those tides may flex the interior and outer layers. If the orbit is not perfectly circular, the changing gravitational pull during each orbit can repeatedly squeeze and relax the planet. That mechanical stress creates heat through internal friction, so the star may warm the planet twice, once from the outside with radiation, again from the inside through tides. It is difficult to maintain modesty under such circumstances. This extra heat may help explain why some close-in giant planets remain bloated long after they should have cooled and contracted. Planetary evolution is not merely about age. It is about energy balance, how much heat is gained, how much is lost, how quickly structure responds. WASP-193b seems to live where incoming energy refuses to be ignored. Then there is atmospheric escape. Stars emit not only visible light but ultraviolet and X-ray radiation, especially in active phases. These energetic photons can heat upper atmospheres strongly. On a low-density planet with weaker outer gravity, particles may reach escape velocities more easily. In simple terms, the star may slowly strip the planet while also inflating it. That sounds rude, but celestial relationships are often complicated. Some exoplanets appear to trail escaping gas, forming comet-like tails. Others may lose mass more quietly over immense timescales. If WASP-193b is shedding atmosphere, it may be doing so over millions or billions of years. Slow enough to remain recognizable now, fast enough to matter eventually. This raises an intriguing possibility. We may be observing the planet during a temporary era. Perhaps it was once denser and more massive. Perhaps it was once even puffier. Perhaps in the distant future it will become smaller after long atmospheric loss. Planets, like stars, have biographies. We usually meet them mid-story. The host star itself deserves respect in this puzzle. Without understanding WASP-193, scientists cannot properly understand the planet. Stellar mass determines orbital properties. Stellar radius helps determine transit-based planetary radius. Stellar luminosity controls received energy. Stellar age constrains evolutionary history. Stellar metallicity, meaning abundance of elements heavier than hydrogen and helium, may influence how planets formed in the first place. The star is both lighthouse and ruler. Everything about the planet is measured partly through it. This is a recurring truth in exoplanet science. To know the child, study the parent. Our own solar system teaches similar lessons. The sun-shaped planetary temperatures, chemistry, migration histories, and habitability. Move Earth inward too far and oceans vanish. Move it outward enough and they freeze. Place Jupiter close to the Sun and it would become an entirely different spectacle. Location transforms identity. For WASP-193b, location may be destiny. Close stars also make discovery easier. A short orbital period means frequent transits. Frequent transits provide many chances to detect dips in brightness. So the very intimacy that makes the planet extreme also made it easier for us to find. That is pleasantly ironic. Its uncomfortable orbit helped introduce it to the universe. There is something almost literary in these systems. A giant world drawn too near its star, swollen by heat, pulled by tides, struggling to retain atmosphere, completing quick orbits in constant exposure, yet still enduring. No romance should be inferred. Stars are not sentimental. They burn hydrogen and keep schedules. Still, the phrase "close and intense relationship" feels earned. Tonight, perhaps as your own room settles into quiet shadows, consider how many identities depend on surroundings. Water freezes here, boils there. A seed thrives in one soil and fails in another. A planet far from its star may cool into compact calm. The same planet brought inward may become a swollen puzzle. Context changes everything. Astronomy repeats this lesson endlessly. There is no single template for worlds. There are only materials, forces, distances, and time combining in different ways. And so WASP-193b circles on, shaped every hour by the star beside it. Its atmosphere likely heated, its structure influenced, its future slowly rewritten orbit by orbit. Across the quiet machinery of a distant planetary system, WASP-193b keeps time in a way that would make our calendars feel almost embarrassingly relaxed. Here on Earth, a year feels like a large container. It holds seasons, birthdays, holidays, deadlines, weather changes, half-finished plans, and at least one drawer we promise to organise before December. A year gives us enough room to notice the slow tilt of sunlight across the walls, the return of certain birds, the changing smell of the air, the familiar rhythm of winter becoming spring, then summer, then autumn, then somehow winter again while we were apparently busy looking for matching socks. But on WASP-193b, a year is not a long sweep around a gentle sun. It is a sprint. This enormous, airy planet completes one orbit around its star in only about 6.25 Earth days. That means that while we're still deciding what to cook next week, this planet has already finished another full lap around its sun. While a single week passes in your room, with perhaps a few cups of tea, a work day or two, some laundry quietly multiplying in the corner, and the usual mystery of where time went, WASP-193b has nearly completed an entire planetary year. NASA's exoplanet catalogue lists its orbital period at about 6.2 days, and the discovery work describes the transit signal as repeating every 6.25 days. That is not merely short, that is astonishingly close and fast by the standards of our own solar system. For comparison, Mercury, the innermost planet around our Sun, takes about 88 Earth days to complete one orbit. Mercury already feels like the speedy one in our neighbourhood, racing close to the solar furnace while the outer planets take their grand, slow walks. Then exoplanets come along and show us worlds with years measured not in months but in days, and sometimes even hours. It is a helpful reminder that our solar system, lovely though it is not the universe's full menu. It is more like one table in a very large restaurant. A 6.25-day orbit tells us immediately that WASP-193b travels close to its host star. The NASA catalogue places its orbit at roughly 0.067 astronomical units, meaning it circles far nearer to its star than Mercury does to our Sun. An astronomical unit is the average distance from Earth to the Sun, which is about 150 million kilometres or 93 million miles. So 0.067 astronomical units is only a small fraction of Earth's distance from the Sun. That closeness matters for almost every part of this planet's story. It affects how much energy the planet receives. It affects its temperature. It affects its atmosphere. It affects how quickly it moves. It affects how strongly the star's gravity tugs and flexes it. And it may help explain why this world is so strangely inflated. When a planet orbits close to a star, it must move quickly to avoid falling inward. Orbital speed is not simply a personality trait. It is a balance. The star's gravity pulls inward, and the planet's sideways motion carries it forward. Together these create an orbit. Closer planets feel stronger stellar gravity, so they must travel faster. This is why Mercury moves faster than Earth. This is why hot Jupiters whip around their stars in only a few days. and this is why WASP-193b lives with a year shorter than many people's vacation plans. There is a strange mental shift required here. We usually think of a year as something connected to climate, memory, and life. A year on Earth is long enough for nature to repeat itself, for trees to change, for school calendars to begin and end, for people to make optimistic resolutions and then quietly renegotiate them by February. But scientifically, a year is just one complete orbit, nothing more. A planet does not need seasons to have a year. It does not need snow, harvests, tax forms, or confused relatives asking what you're doing with your life. It simply needs to go once around its star. By that definition, WASP-193b is extremely busy. Every 6.25 days it returns to the same position in its orbit. From the perspective of a patient astronomer on Earth, its transit repeats. The star dims slightly again. The signal returns like a metronome from deep space. This repeating transit is exactly what helped reveal the planet in the first place. A short orbital period is useful to planet hunters because it gives them more chances to observe transits. If a planet takes 12 years to orbit, like Jupiter does around our Sun, then catching several transits would require rather a lot of patience, and perhaps a very long grant proposal. But if a planet orbits every few days, transits repeat often enough to confirm patterns far more easily. So the same close orbit that heats and stresses the planet also helped announce its existence. That is a recurring theme in astronomy. The very conditions that make an object extreme may also make it detectable. Of course, a short year does not necessarily mean the planet spins quickly. Orbit and rotation are different motions. Earth takes 1 year to orbit the Sun, and about 24 hours to rotate once. On close-in exoplanets, however, rotation may be strongly influenced by tides. Many worlds orbiting near their stars are expected to become tidally locked over time. If WASP-193b is tidally locked, then one side may always face the star, while the opposite side remains turned away. In that case, the idea of a day becomes stranger than the year. The planet's year may be 6.25 Earth days, but its sky could be divided into permanent day and permanent night. One hemisphere receives relentless starlight, the other faces the dark. Between them lies a boundary region, a constant twilight zone where the star would hover near the horizon, neither rising nor setting in the familiar way. Now imagine this on a planet with a vast, swollen atmosphere. The day side is heated continuously. Gas expands, air rises, winds may carry heat toward the night side. The night side cools relative to the day side, though on a thick gas planet heat can be redistributed by powerful circulation. Jet streams may race around the world. Atmospheric waves may travel through layers. Clouds and hazes may form, shift, evaporate, and reform in patterns we cannot yet describe with confidence. A year of only days does not produce a quiet life for a planet. It produces urgency in the physics. Yet that urgency unfolds at planetary scale, which is not the same as human urgency. There are no appointments, no inbox, no little planet-sized alarm ringing every 6.25 days saying, "Congratulations, another orbit completed." There is only motion. Round and round the planet follows its path, held by the star's gravity, warmed by its radiation, tugged by tides, and carried through space with steady precision. The closeness also means the planet receives far more stellar energy than it would if it orbited farther out. That incoming energy is central to understanding why WASP-193b is so puffed up. The discovery paper notes that standard models of irradiated giant planets struggle to reproduce its observed radius, even considering the intense irradiation. In other words, being close to the star helps explain the inflated size, but may not fully solve the puzzle. That is important. If all inflated planets could be explained simply by saying they are close to their stars, this story would be much shorter, though perhaps less pleasant. But the universe is rarely satisfied with one neat explanation. WASP-193b appears to need more than ordinary heating. It may require unusual composition, internal heat, atmospheric opacity, tidal effects, delayed cooling, or some combination still being untangled. The short year is not the whole answer. It is one piece of the answer. Still, it is a major piece. A close orbit means the planet is not living in a calm outer region like Saturn. It is not basking gently at a distance. It is close enough that its star dominates its environment. The planet's atmosphere is exposed to strong radiation. Its upper layers may be stretched and heated. Its orbital motion is rapid. Its long-term future may include atmospheric escape. This makes its survival more interesting. If the atmosphere is so extended and if the star is so close, then how does the planet keep looking this way? Why has it not lost more gas? How long can it remain so swollen? Is it in a stable state, or are we seeing a temporary phase in its evolution? A 6-day year becomes not just a fact but a clue. It tells us the planet's environment is intense. It tells us the star is near. It tells us heating must be strong. It tells us the planet may be tidally influenced. It tells us atmospheric escape may matter. It tells us the story is still changing. There is something almost tender about how much can be learned from timing. A dip in starlight repeats every 6.25 days. From that rhythm, astronomers infer an orbit. From the orbit, distance. From the distance, irradiation. From irradiation, atmospheric expansion. From expansion, questions about density and formation. One repeated flicker becomes an entire world. That is the quiet beauty of transit astronomy. It is also a reminder that the universe often reveals itself through rhythm. Pulsars blink. Variable stars brighten and dim. Moons eclipse planets. Planets cross stars. Galaxies rotate. Even the expansion of the universe is read through patterns in light. Timing is one of science's oldest tools. Ancient observers tracked the seasons and phases of the moon. Modern astronomers track transits across distant stars. The instruments have changed, but the habit remains. Watch carefully, notice repetition, and let the pattern speak. For WASP-193b, the pattern speaks quickly. Every few Earth days it passes between its star and us, from our line of sight. Each transit is a chance to measure. Each one blocks a small amount of light. Each one confirms that the planet continues its tight path. And with each orbit, the planet receives another full cycle of stellar heating. Another lap through radiation. Another pass through tidal influence. Another repetition of an extreme life. Now the phrase "a year that lasts only days" may sound almost playful, but it has serious implications for planetary climate. On Earth, seasons arise because our planet's axis is tilted relative to its orbit. Different hemispheres receive different sunlight across the year. The year is long enough for these changes to unfold gradually. On a close-in giant like WASP-193b, seasons may not resemble anything familiar. If the orbit is nearly circular and the planet is tidally locked, the dominant climate pattern may be permanent day-night contrast rather than seasonal cycling. If the orbit has even slight eccentricity, stellar heating may vary across the orbit, creating rhythmic pulses of energy. Even small orbital details can matter when the planet is so close to its star. Eccentricity, inclination, tidal alignment, atmospheric circulation, radiative timescales. These are not decorative terms. They determine how heat moves, where clouds form, how winds behave, and how strongly the planet changes over time. A short year compresses orbital change into a rapid cycle. But for the planet, this is normal. That is another gentle lesson from astronomy. Normal depends on where you live. Earth's year feels natural to us because we evolved within it. Our biology, agriculture, cultures, calendars, and habits all grew under a 365-day orbit. We built festivals around seasons. We measure age in years. We schedule plans by months. We experience time through Earth's movement. but another planet's year could last 6.25 days, or 12 years, or 165 years like Neptune, or mere hours for some ultra-short period worlds. There is no universal year. There is only local motion. Perhaps that is a soothing thought in its own way. The cosmos does not force one rhythm on everything. Each world keeps time according to its own orbit. Some move slowly through vast cold distances. Others hurry close to fire. Some drift in systems with multiple stars. Some may wander without stars at all, carrying no year in the ordinary sense. WASP-193b keeps a quick rhythm. Fast, close, heated, and strange. If you were somehow watching from a safe distance, perhaps from a fictional observatory parked high above the system, you would see the planet sweep around its star again and again. Its path would be tight compared with the broad orbits we know. Its star would loom large. The planet's atmosphere, extended and fragile-looking, would move through fierce light with each lap. There might be no leisurely winter, no quiet spring, only continuous stellar exposure. The planet's year is not a cycle of seasons. It is a cycle of survival. And yet, despite this intensity, there is stability in the repetition. The orbit is predictable enough for astronomers to measure. The transits return. The period holds. The system follows the rules of celestial mechanics with calm indifference to our surprise. That combination is lovely. Extreme but orderly. Strange but measurable. Unfamiliar but governed. Science often finds comfort there. The universe can be bizarre without being chaotic. It can produce planets that seem absurd while still obeying gravity, thermodynamics, and orbital mechanics. It can make a cotton candy planet with a 6-day year, and then let us understand it one measurement at a time. Not every planet suffers politely. Some worlds endure cold silence in distant darkness. Some keep temperate balance. Some rotate beneath mild skies and modest sunlight. And then there are planets like WASP-193b, living so near their star that heat becomes one of the main authors of their identity. This is where the story turns from odd measurements to physical consequences, because a giant planet with a very short year is not merely close to its star in an abstract orbital sense. It is close enough that radiation arrives in overwhelming abundance. Day after day, orbit after orbit, stellar energy pours into the atmosphere. That energy changes structure, chemistry, winds, and perhaps the entire appearance of the world. If the earlier chapters of this mystery involved mass and density, this part involves temperature and expansion. Heat is not decoration. Heat reshapes matter. We know this intimately on Earth. Metal expands in warmth. Air rises when heated. Ice melts, water evaporates, bread dough swells in an oven with suspicious confidence. Temperature alters behaviour everywhere. Scale that principle up to planetary size, and things become dramatic. For WASP-193b, its close orbit means intense irradiation from the host star WASP-193. The exact equilibrium temperature depends on reflectivity, atmospheric circulation, absorption, and other details, but broadly speaking, this is a hot world by ordinary standards, not molten rock hot in the same way as some ultra-scorched lava planets perhaps, but certainly hot enough that hydrogen-rich atmospheric layers respond strongly. And hydrogen, being light and mobile, does not need much encouragement. Warm hydrogen expands. Hot hydrogen expands enthusiastically. A giant atmosphere composed largely of hydrogen and helium can therefore become swollen under constant stellar heating. Gas particles move faster, pressure support changes, upper layers rise farther from the core, the planet's visible radius increases. This is one reason astronomers refer to some worlds as inflated hot Jupiters or superpuffs. They are larger than expected because incoming energy helps keep them expanded. In simpler terms, the star may be blowing up the planet like a slow-motion balloon, with more physics and fewer party hats. Now, not all close giant planets become as extreme as WASP-193b. Many hot Jupiters are heated, yes, but still denser and more compact than this world. That tells us stellar heat alone may not explain everything. Still, it is likely one of the central forces in the story. Imagine taking Jupiter and moving it far inward toward the Sun. Suddenly the sunlight becomes fierce, atmospheric temperatures rise, outer layers puff outward, the chemical environment changes, weather patterns intensify. It would not become identical to WASP-193b, but it helps illustrate how much location matters. Planets are not defined only by composition, they are defined by environment. The same broad ingredients placed in a different orbit can create a different world. There is another subtle point worth appreciating. When astronomers measure the radius of a transiting exoplanet, they are not measuring a solid surface. They are measuring the altitude where the atmosphere becomes opaque enough to block starlight effectively. That means if the atmosphere is very extended, the planet appears larger. This is especially important for hot, low-density planets. Their edge may lie high in tenuous gas layers, so part of the bloated appearance of WASP-193b may come from a vast upper atmosphere stretched outward by heat. Not fake size, real atmospheric extent, but extent nonetheless. It is rather like measuring a person by including an extravagant winter coat and several inches of hair. Accurate in one sense, revealing in another. Now, let us consider the weather. On a close-in gas giant, especially one likely tidally locked, one hemisphere may face the star continuously. That day side receives relentless radiation. Temperatures soar higher there than on the night side, though thick atmospheres can transport heat around the globe. This creates planetary-scale winds. Gas rises on the hot side, flows toward cooler regions, sinks elsewhere, then circulates again. Jet streams may race at astonishing speeds. Shock fronts, waves, and layered circulation patterns may emerge. Weather on Earth can ruin a picnic. Weather on hot giants can rearrange atmospheric continents of gas. For a fluffy planet, these winds may move through especially extended layers. The atmosphere has more vertical room, more gradients, more complexity. Heat transport becomes a grand engineering project run entirely by fluid dynamics. No committee meetings, no budget delays, just motion. Then there is chemistry. At elevated temperatures, molecules behave differently. Some compounds remain gaseous that would condense elsewhere. Clouds may form from materials that sound improbable in everyday weather reports. Silicates, metal oxides, sulfides, alkali vapors, exotic hazes. A cloud on Earth might bring rain. A cloud on a hot exoplanet might involve vaporized minerals deciding to regroup. We do not yet know every atmospheric detail of WASP-193b, but the principle stands: heat transforms chemistry. This is why telescopes that analyze atmospheric spectra are so valuable. During transits, a tiny portion of starlight passes through the planet's atmosphere. Different molecules absorb different wavelengths. By studying that filtered light, astronomers can infer atmospheric composition. For a bloated planet, the large atmospheric scale height may actually help such measurements. More extended atmospheres can produce stronger spectral signals. So the very puffiness that confuses theory may aid observation. Nature occasionally compensates. Still, heat is not only expansion, heat can also mean loss. When upper atmospheric layers absorb enough energetic radiation, particles can gain sufficient energy to escape the planet's gravity. This is especially relevant for hydrogen, the nimble acrobat of the periodic table. Thus, a close hot planet may simultaneously inflate and evaporate. Its atmosphere swells outward while some of it leaks away into space. That sounds contradictory, but it is common in planetary physics. Systems often expand locally while diminishing globally. Think of steam rising from a kettle. Larger above, less below. Over millions or billions of years, atmospheric escape may significantly alter a planet. Some worlds may lose enough gas to become different categories entirely. A once Neptune-like world might become a stripped rocky core. A puffed giant might slowly contract as mass is lost and heating changes. For WASP-193b, one possibility is that we are seeing a temporary stage. Perhaps it is caught in a bloated era. Perhaps it was denser in youth. Perhaps it will be smaller in old age. Astronomy often meets objects mid-biography. We infer childhood and old age from current clues. Another factor in inflated planets may be delayed cooling. Young giant planets begin hot from formation. Normally they radiate that heat into space over time and gradually shrink. But if stellar irradiation or atmospheric opacity traps heat efficiently, contraction can slow. Imagine trying to cool off while wrapped in too many blankets beside a fireplace. The process lacks urgency. If WASP-193b retains internal heat while receiving external heat, its swollen state may persist longer than naive models predict. There is also tidal heating. If the orbit has even modest eccentricity, the changing gravitational pull from the star can flex the planet rhythmically. Internal friction converts that motion into heat. This mechanism powers volcanic activity on Io in our solar system. Scale similar ideas to giant exoplanets, and extra heat may contribute to inflation. So the bloated atmosphere could be supported by several furnaces at once: starlight above, residual heat within, tidal kneading below. No wonder the planet appears oversized. There is something wonderfully humbling in how much of planetary identity depends on energy flow. We often think of planets as static objects, balls of matter placed in orbit. But planets are processes. They cool, warm, circulate, lose gas, migrate, contract, expand, weather, and evolve. They are not sculptures. They are ongoing events. WASP-193b demonstrates this beautifully. Its unusual radius is not just what it is what is happening. Tonight, perhaps as your own room settles into a comfortable temperature, and your body appreciates the luxury of modest atmospheric conditions, consider what it means for a world to live too close to fire. No cool outer calm, no gentle distant sunlight. Instead, constant exposure. A star large in the sky, heat pressing into the upper layers, winds redistributing energy around the globe, gas swelling outward, particles escaping upward. A planet made larger by the very force that may slowly erode it. That tension gives the world character. It is both sustained and threatened by its star, expanded and vulnerable, magnified and worn down. Many systems in nature carry such dual truths. The same sunlight that nourishes can also parch. The same pressure that strengthens can also fracture. The same closeness that warms can also overwhelm. Perhaps this is why the phrase bloated atmosphere feels more interesting than it first appears. It is not merely size, it is evidence of relationship. The star has left fingerprints all over the planet. How do planets usually form? And why does WASP-193b seem to ignore some of the usual rules? Before a planet becomes strange, it first has to become a planet at all. That may sound obvious, but it is worth pausing over. Every world, whether rocky like Earth, ringed like Saturn, giant like Jupiter, or puzzling like WASP-193b, begins in a place of dust, gas, collisions, gravity, and remarkable patience. Planets are not carved whole from cosmic stone. They grow, they gather, they survive. They compete with neighbouring bodies for material. They migrate, they collide, they lose things, they gain things. They emerge from chaos looking, if we are lucky, almost organised. To understand why WASP-193b seems to break the rules, we first need to understand what the usual rules are supposed to be. That story begins with stars. When a new star forms, it does not use every bit of surrounding material. Much of the gas and dust collapses inward to ignite the star, but some remains in a spinning disk around it. This is called a protoplanetary disk. Picture a flat swirling disk of leftovers around a newborn sun. That is where future planets begin. Within that disk are tiny dust grains, ices, silicates, metals and gases. At first, these particles are microscopic. They collide gently, stick together, grow into pebbles, then boulders, then kilometre-scale bodies called planetesimals. Once things become kilometre-sized, collisions grow more dramatic. The universe loves escalation. Planetesimals pull on one another through gravity. Some merge, some shatter, some are flung elsewhere. Over time, larger bodies dominate their neighbourhoods, sweeping up material like determined vacuum cleaners with orbital rights. From these growing embryos, planets emerge. That broad framework is accepted and supported by many observations and simulations, though details remain gloriously complicated. Now, rocky planets such as Mercury, Venus, Earth, and Mars form mainly in the hotter inner regions of disks, where lighter volatiles are less stable and solid materials dominate. Farther out, beyond what is often called the snow line, temperatures drop enough that water ice and other frozen compounds can survive. That adds much more solid building material. This is important. More solids mean faster growth of large cores, and large cores may then begin attracting huge envelopes of hydrogen and helium gas before the disk disperses. That is the leading explanation for gas giants like Jupiter and Saturn. This process is known as core accretion. First build a heavy core, then gather gas rapidly, then become impressive. It is an excellent strategy. There is another proposed route for some giant planets called disk instability, where parts of the disk collapse gravitationally into giant clumps directly. But for many known planets, core accretion remains the standard model. Now let us return to WASP-193b. This world appears very large in radius, but unusually low in mass and density. It also orbits close to its star. Those traits together make the ordinary formation story less straightforward. Why? Because if a planet grows a sufficiently large core and gathers lots of gas, one often expects a fairly substantial giant planet. Strong gravity compresses the gas envelope. Over time, the planet cools and contracts. Yet this object appears swollen, airy, and relatively light for its breadth. That means one or more pieces of the usual story may need adjustment. Perhaps the core formed, but not very large. Perhaps gas was gathered, but under unusual thermal conditions. Perhaps the planet formed farther out and later migrated inward. Perhaps atmospheric heating after migration inflated it dramatically. Perhaps mass was lost later. Perhaps several processes cooperated with suspicious efficiency. When planets become strange, single cause explanations often become lonely. Let us examine the first puzzle. How do you become giant-looking without becoming giant-heavy? A large radius suggests an extensive gaseous envelope, but low mass suggests that envelope does not contain as much matter as similar-sized giants. This could mean the planet acquired gas, but not in overwhelming quantity. If the envelope is hot and extended, it can occupy great volume without enormous mass. That is rather like a duvet with very enthusiastic fluffing. Still, building even a modest giant envelope requires timing. Protoplanetary disks do not last forever. Gas around young stars disperses over a few million years. If a core waits too long, the gas supply dwindles. So to form a gas-rich planet, the core generally must grow quickly enough while gas remains available. This suggests WASP-193b may have formed efficiently in its youth. Then came migration. Many close-in giant exoplanets likely did not form where we see them now. Near a star, conditions can make giant formation difficult, because the inner disk may contain less solid material and high temperatures complicate matters. Instead, a giant may form farther out, where ices help core growth, then move inward through interactions with the disk or with other planets. Migration is one of the great revelations of exoplanet science. Our early solar system-centered intuition assumed planets mostly stay where they form. The galaxy replied, sometimes. A planet can exchange angular momentum with surrounding disk material and spiral inward gradually. It can also be perturbed by neighbouring planets into eccentric paths later circularised closer to the star. So WASP-193b may have been born in a cooler outer region, then relocated to a much hotter neighbourhood. That move changes everything. Close to the star, irradiation intensifies, atmospheres heat and expand, tidal effects increase, escape processes become important. A once ordinary gas-rich world may become inflated and transformed. This is why formation and current appearance are not the same question. Where a planet began may differ sharply from what it looks like now. There is another challenge too. Why did it remain so low density? Even if migration and heating explain inflation, giant planets tend to cool and contract over time. Gravity is patient and persuasive. Unless energy continues to support the atmosphere, swelling should diminish. That means either the planet receives enough stellar energy to stay expanded, or additional internal processes help maintain the puffed state, or our models of these worlds need refinement. Possibly all three. Some researchers investigate opacity within atmospheres. If heat escapes inefficiently because atmospheric layers trap radiation, cooling slows. The planet stays larger longer. Others consider tidal heating from ongoing orbital effects. Others model unusual heavy element distributions inside the planet. Others ask whether observed radii probe especially high atmospheric layers. Every strange world creates employment for theorists, and this one seems particularly generous. There's also a cautionary lesson here about the phrase breaks the rules. Nature is not violating physics. No law has been suspended. No emergency meeting of gravity has been called. Rather, the planet breaks simplified expectations. It resists easy versions of the models. It sits near edges of known parameter space and asks whether our summaries are too tidy. This happens often in science. The first stars seemed fixed until they were found to move. Atoms seemed indivisible until they were not. Continents seemed stationary until they absolutely were not. Planets seemed like our planets until exoplanets introduced hot Jupiters, mini Neptunes, lava worlds, super-Earths, and super-puffs. Reality is usually more varied than first drafts allow. There is something deeply comforting in that. Knowledge grows not because we guessed perfectly, but because the universe keeps correcting us. Now imagine the young system around WASP-193 billions of years ago. A disk of gas and dust circles the newborn star. Particles collide and stick. Pebbles become boulders. Boulders become planetesimals. One growing core gathers strength beyond the snow line perhaps, where icy solids are plentiful. Gas begins to collect. The world swells. Orbital interactions nudge it inward over time. Closer to the star, heating intensifies. The atmosphere expands further. Mass loss may begin slowly. The object we now call WASP-193b emerges from a long chain of events, not a single dramatic moment. This perspective matters. When we see a strange planet, we are often seeing history compressed into one snapshot. Its density reflects formation. Its orbit reflects migration. Its atmosphere reflects current heating. Its future may involve escape and contraction. One measurement can contain several eras. That is part of the beauty of planetary science. The present is readable if you know what to ask. Perhaps as you listen tonight there is a useful parallel in everyday life too. What something looks like now rarely explains how it got there fully. Histories matter, paths matter, pressures matter, timing matters, even planets carry biographies. And some biographies are delightfully complicated. Some discoveries arrive with their own explanation neatly folded inside them. A rocky planet near a star is hot, sensible enough. A distant icy body is cold, fairly straightforward. A moon orbiting a giant planet obeys gravity. Everyone nods politely. Then a world like WASP-193b appears, carrying the radius of a giant, the mass of something lighter than expected, the density of spun sugar, and the calm confidence of an object that has no interest in making our models comfortable. That is when theories begin gathering. Not because science is confused in a helpless way, but because science is doing exactly what it should do. When reality presents a puzzle, researchers propose mechanisms, test them, compare predictions, refine assumptions, and gradually narrow the field. This is one of the healthiest habits humanity has ever developed. Instead of shouting at the planet for being inconvenient, we ask better questions. So what might explain WASP-193b? No single answer has yet marched into the room wearing certainty. Instead, several ideas likely contribute, overlap, or compete. The truth may be one dominant process, or several working together like a committee of suspicious efficiency. Let us begin with the most obvious suspect: stellar heating. Because WASP-193b orbits close to its host star, WASP-193, it receives intense radiation. That incoming energy can heat the upper atmosphere, causing gases to expand. Hydrogen and helium, already light and willing to occupy space, become even more spread out when warmed. This can increase the planet's measured radius significantly. Think of a loaf rising in an oven, except the loaf is planetary, the oven is nuclear fusion, and no one has remembered to set a timer. Inflation by irradiation is a real and well-studied phenomenon. Many hot Jupiters are larger than basic cooling models would predict, because starlight alters their atmospheres and internal heat balance. So the first theory says, perhaps WASP-193b is simply an extreme case of a known process. That helps, but often not enough. Because some planets remain larger than stellar heating, alone seems able to explain, which leads to theory number 2, delayed cooling. Young giant planets begin hot after formation. Over time, they radiate that heat into space and gradually contract. If something interferes with that cooling, the planet can remain puffed up for longer than expected. What might interfere? A thick atmosphere with high opacity can trap outgoing heat. Certain chemical mixtures, clouds, hazes, or internal structures may act like insulation. Energy leaks away more slowly. Contraction slows. The world remains oversized. In everyday terms, it is difficult to cool off while wrapped in blankets beside a fireplace. For WASP-193b, some researchers suspect that trapped heat may be helping preserve its swollen state. Then we come to tidal heating. This theory is wonderfully physical and slightly rude. If the planet's orbit is not perfectly circular, the gravitational pull from the star changes subtly throughout the orbit. That changing pull flexes the planet. Stretch, relax, endlessly. Internal friction from this repeated deformation generates heat. A smaller version of this happens in our own solar system with Io, whose intense volcanism is powered largely by tidal flexing from Jupiter and neighbouring moons. Scale the idea to a giant close-in exoplanet, and tides may become a hidden furnace. If WASP-193b experiences even modest tidal heating, it could help support atmospheric inflation from below while the star heats it from above. 2 furnaces are often more persuasive than one. Another important theory concerns composition. Not all giant planets are built the same way. 2 worlds with similar masses can have different internal structures depending on core size, heavy element content, and how those materials are distributed. One planet may have a dense, massive core and compact envelope. Another may have a smaller core and a more extended gas layer. Heavy elements mixed throughout the envelope can also change thermal transport and contraction behaviour. So perhaps WASP-193b is not merely heated. Perhaps it was assembled differently. If it formed with a relatively modest core and a large hydrogen-helium envelope, it may naturally occupy more space for its mass than denser cousins. This is less dramatic than physics broken, but often more useful. Nature loves structural differences. There is also the migration theory, which is less about what the planet is and more about where it used to be. Many close-in giant exoplanets likely formed farther from their stars, where cooler temperatures and abundant icy solids made giant planet formation easier. Later, interactions with the protoplanetary disk or neighbouring planets moved them inward. If WASP-193b formed in a colder outer region, then migrated close to the star, it may have undergone two very different life phases. Phase 1. Formation in a calmer nursery. Phase 2. Relocation into an irradiated furnace. That transition could dramatically reshape the atmosphere. A once ordinary gas-rich planet might become inflated after moving inward. Migration explains many exoplanet oddities because it reminds us that current location is not birthplace. Planets can move houses, sometimes to neighbourhoods they were never emotionally prepared for. Now let us discuss atmospheric escape, because it sounds destructive and may also be informative. Close stars emit ultraviolet and X-ray radiation that can heat upper atmospheres strongly. On low-density planets, gas may escape into space over long time scales. This can strip envelopes, reshape composition, and alter radius evolution. At first glance, that seems opposite to explaining a puffed planet. If gas is escaping, should the planet not shrink? Eventually, perhaps yes, but transitional states matter. A planet can be highly extended while also losing atmosphere. We may be observing WASP-193b during such a stage, still large, still inflated, but slowly changing. This is one of astronomy's recurring themes. We often meet worlds mid-transformation. There is another subtle theory involving observational geometry and atmospheric measurement itself. When astronomers derive radius from a transit, they measure where the atmosphere becomes opaque enough to block starlight. If a planet has a very hazy or extended upper atmosphere, the measured radius may correspond to a high-altitude layer rather than a deeper, physical boundary. That does not mean the radius is wrong. It means the edge of a gas giant is more like a fading fog than a solid wall. So part of the enormous size may reflect where light is stopped, rather than where dense material begins. This is important for fluffy planets generally. They may wear very large visible outlines. Some researchers also explore ohmic heating, one of the more delightfully technical explanations. In strongly irradiated planets, atmospheric winds move through magnetic fields. That motion can induce electric currents. Those currents dissipate energy as heat inside the planet. Yes, a distant gas giant may be warmed partly by atmospheric electricity. The universe occasionally shows off. Ohmic heating has been proposed for some inflated hot Jupiters, though whether it explains any specific planet depends on magnetic field strength, conductivity, wind structure, and many details that ensure graduate students remain employed. Could it help with WASP-193b? Possibly as part of a combined picture. And combined pictures may be the most realistic outcome. Science often begins by asking which single mechanism explains this, then matures into several mechanisms probably contribute. That may be where this planet belongs. Imagine the recipe. A relatively low-mass, gas-rich world forms farther out. It migrates inward. Stellar heating inflates the atmosphere. Cooling slows due to opacity or structure. Tidal effects add heat. Perhaps magnetic interactions contribute. Some gas escapes. The remaining envelope stays remarkably extended. No one ingredient is enough. Together they create the observed puzzle. There is something elegant about that. Complex outcomes from layered causes. Human beings often prefer one clean explanation because it fits nicely in the mind. But nature frequently prefers several overlapping influences. Weather is not caused by one thing. Health is not caused by one thing. History is not caused by one thing. Neither are planets. What makes WASP-193b especially valuable is that it pushes these theories to their limits. Mildly unusual planets can be explained many ways. Extreme ones expose which models truly work. If your theory explains ordinary cases but fails spectacularly here, it may need revision. That is not failure. That is progress-wearing work boots. There is also humility in this stage of science. We know enough to identify the puzzle. We know enough to model plausible causes. We do not yet know enough to claim final certainty. That middle ground is where much of real research lives. Not ignorance, not complete mastery. Careful movement between the two. Perhaps tonight, as your own thoughts slow into gentler shapes, there is comfort in remembering that unanswered questions are not empty spaces. They are active places where understanding is being built. Somewhere far away, a star shines on a world too light for its size. Here, people compare equations, telescope data, atmospheric models, and interior structures trying to explain it. The planet simply continues orbiting. If planets held family reunions, some tables would be easier to organise than others. Rocky worlds might gather in one corner comparing craters, mountains and unfortunate impacts. Ice giants could discuss atmospheric colours with measured dignity. Dwarf planets would perhaps insist on badges clarifying several unresolved feelings. And then, somewhere under a banner that reads large, gaseous and complicated, you would find the gas giants and their increasingly peculiar relatives. That is where WASP-193b would likely be standing, perhaps slightly overdressed in atmosphere. Because one of the most important lessons from exoplanet science is that giant planets are not one tidy category. Before we discovered worlds around other stars, our own solar system gave us 4 broad planetary types to work with: rocky inner planets, gas giants, ice giants, and smaller icy leftovers. It was a useful local sample, but still only a sample. Then thousands of exoplanets began arriving. Suddenly the old categories stretched. We found hot Jupiters, warm Neptunes, mini-Neptunes, super-Earths, lava worlds, ocean candidates, ultra-short period planets, and low-density objects so inflated they sounded fictional. The giant planet branch of the family tree became especially lively. So where does WASP-193b belong? To answer that, we should start with familiar giants. In our solar system, Jupiter is the archetype. It's massive, broad, hydrogen-rich, deeply gravitational, with powerful weather systems and an interior compressed by its own weight. Jupiter is so dominant that it shapes asteroid belts, influences comet paths, and generally behaves like the largest person in the room. Saturn is another gas giant, lighter in average density, ringed magnificently, but still substantial. Its mass, size, and structure fit comfortably within the expected range of giant planets, built from hydrogen, helium, and deeper, heavier material. Then we have Uranus and Neptune, often called ice giants. They contain more heavy volatiles such as water, ammonia, and methane in their deep compositions, with comparatively smaller hydrogen-helium envelopes than Jupiter and Saturn. Already, even in our own system, giant means several different things. But exoplanets complicated matters beautifully. Astronomers began finding planets with masses similar to Jupiter, but orbits lasting only a few days. These became known as hot Jupiters. They likely formed farther out, then migrated inward. Their close proximity to stars meant high temperatures, tidal effects, and atmospheric inflation. Some were larger than Jupiter, despite similar or smaller masses. That was our first clue that environment could reshape giant planets dramatically. Then came stranger members of the family. Planets with sizes comparable to Neptune or larger, but density so low that ordinary expectations started muttering in the hallway. These worlds became known informally as super puffs. The nickname is charming, but scientifically meaningful. Super puffs are planets with unusually large radii for their masses, resulting in extremely low average densities. Many are rich in hydrogen-helium envelopes, and may possess extended atmospheres strongly affected by stellar heating. They are the overinflated cousins at the reunion. Now, not every super puff is identical. Some are smaller than giant planets, but much puffier than expected. Some orbit in multi-planet systems. Some may have thick hazes that make them appear larger during transits. Some may be transitional worlds gradually losing atmosphere. The category is more family resemblance than strict uniform, and somewhere near the dramatic end of this spectrum sits WASP-193b. Its radius is giant-like, its density is extraordinarily low, its orbit is close, its atmosphere appears highly extended. So while it shares traits with gas giants, it also belongs among the superpuffs and inflated oddities that challenge simple labels. This is why the family tree is strange. Traditional gas giants like Jupiter are massive enough that gravity compresses their interiors significantly. Add more mass to a gas giant, and the radius does not increase endlessly. In fact, beyond certain ranges, additional mass may compress the planet more rather than make it much larger. Gravity becomes an excellent packer, but superpuffs operate in a different regime. Lower mass means less self-compression. Strong stellar heating can expand outer layers. Large atmospheric scale heights can push the observable radius outward. Thus, you can get a planet that looks giant in size without carrying giant-level mass. It is the difference between dense architecture and inflated volume. Imagine two buildings of equal height. One is concrete, steel, and seriousness. The other is mostly atrium. Same skyline, different substance. There is also a historical reason these categories feel messy. Our language developed from what we knew first. Gas giant was built around Jupiter and Saturn. Once exoplanets appeared, we kept reusing old words while stretching them to cover new realities. This happens often in science. Early maps are drawn from local coastlines. Later oceans require revisions. Take mini Neptunes, for example. Our solar system has no direct counterpart to many of these common exoplanets, worlds larger than Earth but smaller than Neptune, often with thick atmospheres. They may be among the most common planet types in the galaxy, yet absent here. That alone is humbling. The universe's common worlds are not necessarily ours. Similarly, our familiar gas giants may be only one branch among many giant-like possibilities. WASP-193b reminds us of this every time someone says planet like Jupiter too casually. It may resemble Jupiter in width, but not in bulk behaviour. Another useful comparison involves atmosphere. Jupiter's atmosphere is deep and dynamic, but the planet's strong gravity keeps structures comparatively compact relative to its mass. On a superpuff, lower gravity and upper layers can allow atmosphere to extend farther outward. This means transit measurements may capture a very large apparent radius at high altitudes. The planet presents itself dramatically. One might say superpuffs are masters of silhouette. There are known examples of low-density exoplanets besides WASP-193b that help define the family. Worlds in systems such as Kepler, 51 host planets so diffuse they became famous for exactly this reason. Those planets showed that extremely low densities were not measurement flukes or isolated accidents. Nature can build these things more than once. That is crucial. One oddball may be a curiosity. Several oddballs become a population, and populations demand theory. So the family tree now includes classic gas giants, massive and compressed, hot Jupiters, giant planets living too near their stars, ice giants, compositionally distinct outer worlds, mini Neptunes, common mid-sized atmospheric planets, superpuffs, low-density inflated bodies, and hybrids occupying blurry borders between categories. Astronomy is increasingly comfortable with blurry borders. Nature rarely uses our filing system. There is also evolution to consider. A planet might not stay in one category forever. A gas-rich sub-Neptune close to a star may lose atmosphere and become a rocky remnant. A young giant may begin inflated, then cool and shrink. A migrated world may transition from temperate outer giant to hot atmospheric oddity. So the family tree is not static. Some branches move, some identities are temporary. WASP-193b may itself represent a stage, not an endpoint. Perhaps it formed as a more standard gas-rich planet and later became highly inflated near its star. Perhaps it is slowly shedding atmosphere now. Perhaps billions of years from now it would look far less dramatic. Planets, like people in old photographs, can be hard to categorize from one snapshot. There is something pleasantly human about our urge to classify, though. We build shelves because shelves reduce anxiety. If we know whether something is a gas giant or a super puff, we feel a little safer. Yet the universe keeps handing us objects that live between shelves. This is not rude, it is educational. Every ambiguous planet forces better definitions. Every strange family member reveals hidden assumptions. Every new category reminds us that discovery is ongoing. Tonight, as you rest in a room whose gravity is familiar and whose atmosphere is behaving with admirable moderation, it may be soothing to imagine that elsewhere giant worlds come in many forms. Some are compact and powerful, some are ringed and stately, some are icy and distant, some race around stars in overheated orbits, some are so airy they earn dessert nicknames, and one of them, WASP-193b, stands among the strangest branches of the giant planet family tree, looking large, weighing lightly, and complicating every reunion. We will leave classification behind and ask a more personal question. If you somehow arrived there, could you stand on such a world at all? Suppose for one peaceful moment that impossible travel has become routine. Your suitcase is packed. Your passport has somehow been accepted by interstellar authorities. A remarkably patient spacecraft has carried you across hundreds of light years, and after a journey involving many naps, several snacks, and at least one dramatic window stare, you arrive near WASP-193b. Naturally, the practical question appears, could you stand on it? This is a wonderfully human question. Whenever we discover a place, we immediately wonder how our feet would feel there. Can we walk on it? Could we land? Is there ground? Would shoes help? Human beings are deeply committed to surfaces. Unfortunately, the universe is under no obligation to provide them, and in the case of WASP-193b, the honest answer is almost certainly no, not in any familiar sense. Because this world is not thought to be a rocky planet with a clear solid crust waiting beneath the clouds. It belongs to the family of giant gaseous planets, worlds dominated by thick envelopes of hydrogen and helium surrounding deeper high-pressure interiors, possibly with a compact core buried far below. That means there may be no ordinary surface where sky ends and ground begins, no shoreline, no mountain path, no convenient landing pad reading visitors welcome. Instead, there is atmosphere, layer after layer after layer. When we imagine planets, we often picture them like Earth. Because Earth is where all our practice occurred, we are used to standing on crust, looking upward through air, with gravity pulling us towards something firm. That model works beautifully here. It does not generalize well. Try to stand on Jupiter, and the same problem appears. Jupiter has cloud tops, storms, deeper atmospheric layers, increasing pressure, rising temperatures, and eventually states of matter so extreme that the word standing loses usefulness. WASP-193b likely offers a similar challenge, but with an even more extended and lower density outer atmosphere. So if you descended toward it, what would happen? At first, from orbit, you would see a large swollen world, probably wrapped in haze or clouds, receiving intense light from its nearby star. Its visible boundary would look like a planet, because from a distance, atmosphere creates clean silhouettes. But silhouettes can be misleading. Approach closer, and you would enter upper atmospheric layers where the gas is thin, hot, and spread across vast altitudes. There is no moment of touchdown, no satisfying little bump beneath landing gear, no airport announcement thanking you for choosing impossible destinations. You simply move deeper into gas. This is one of the strangest ideas for surface-trained minds. A planet can exist without a place to stand. Now, some people then ask, but surely somewhere below there must be something solid. Perhaps. possibly a dense core of rock, metal, ice-rich material, or exotic compressed matter deep inside. Many giant planet models include cores, but if such a core exists, it may lie beneath enormous depths of atmosphere under pressures and temperatures so extreme that reaching it would be less like hiking downward and more like entering a prolonged argument with thermodynamics. By the time you got anywhere near those depths, your spacecraft would have very strong opinions. Pressure increases as you descend because more atmosphere sits above you. On Earth, atmospheric pressure changes modestly over everyday heights. On giant planets, pressure rises relentlessly with depth. 1 bar, 10 bars, hundreds, thousands. Then regimes where familiar materials behave in unfamiliar ways. Hydrogen may become compressed into exotic phases. Temperatures climb, winds may roar, electronics fail, structures deform, insurance paperwork becomes symbolic. So no, you would not casually stand on the core, even if there is one. This raises an interesting distinction between surface and reference level. For gas giants, scientists often define altitudes using pressure levels, such as the level where atmospheric pressure equals 1 bar, roughly similar to Earth sea level pressure. This gives a useful comparison point, but it is not a flaw. It is just a chosen depth in gas. If you hovered there in a craft, instruments might say, "We have reached 1 bar." Your feet would still say, "There is nothing under us." That is science working beautifully and shoes working poorly. Could you float instead? Possibly, for a while, with sufficient technology. Because WASP-193b is so low density overall, people sometimes imagine bouncing on clouds or drifting through softness. It is important to be gentle with that image. Low average density does not mean plush comfort. It means mass spread across large volume. The upper atmosphere may still be hot, windy, chemically hostile and unstable. There may be turbulence, storms, and radiation conditions depending on altitude and stellar activity. You would not be reclining on cosmic cotton candy. You would be surviving in physics. Still, buoyancy is a real concept in atmospheres. If you had a specially designed floating habitat with the right density relative to surrounding gas, then in principle one could float at some atmospheric level, much as balloons float in Earth's atmosphere. This idea has often been discussed more seriously for places like Venus, where certain cloud layer altitudes have surprisingly Earth-like pressure ranges despite other severe problems. For WASP-193b, however, high temperatures and uncertain chemistry make the engineering considerably less cheerful, yet conceptually, floating is more plausible than standing. That sentence alone tells you much about giant planets. There is also gravity to consider. Because WASP-193b is inflated and relatively low in mass for its size, the gravity near its upper atmospheric radius may be lower than many imagine for a giant world. That does not mean gentle enough for tourism necessarily, but it means the pull at the visible surface could be less severe than Jupiter's cloud-top gravity. Again, giant appearance can hide modest grip. So if you hovered in the upper atmosphere, you might experience a gravitational environment not as crushing as the planet's huge size suggests. Then the atmosphere would attempt to compensate with heat and wind. Nature values balance. Now let us imagine the sky. If the planet is tidally locked, one side may always face the star. In that case, from some atmospheric locations, the star would hang fixed in the sky, enormous and bright, never rising or setting. Elsewhere, on the night side, darkness would persist indefinitely, lit perhaps by faint stars and atmospheric glow. Near the terminator, the boundary between day and night, perpetual twilight could reign. These are places where atmospheric circulation may be especially dramatic as heat moves from day to night. Could one stand there on a floating platform? Perhaps in science fiction. It is an attractive image. A station suspended in twilight above endless clouds, star fixed on the horizon, winds humming through support structures. But on the actual planet, conditions would likely be severe enough to humble architecture quickly. There is something revealing in our desire to stand, though. We use standing as shorthand for belonging. If we can stand somewhere, we understand it. We can build there, rest there, claim familiarity. Gas giants deny that instinct. They are places we can study deeply while never quite occupying in the ordinary way, and perhaps that is healthy. Not every destination is meant for footsteps. Some are meant for measurements, some for imagination, some for humility. WASP-193b belongs strongly in that category. Its very nature asks us to loosen Earth-centered expectations. A planet need not have beaches, stones, or cliffs to count as real. It can be mostly atmosphere, with boundaries defined by pressure and opacity rather than ground. That broadens the meaning of world. Our ancestors looked upward and imagined lights. Later generations imagined spheres. Now we know some spheres are rocky, some icy, some metallic, some oceanic perhaps, and some are vast envelopes of gas with no welcoming floor at all. Reality keeps enlarging vocabulary. Would a probe survive descent? Perhaps for a while, depending on engineering and target depth. Humanity once sent the Galileo probe into Jupiter's atmosphere, where it transmitted data during descent before being overwhelmed by pressure and heat. A future probe to a world like WASP-193b might one day sample winds, chemistry, temperature profiles, cloud layers, and atmospheric escape. It might descend not to land, but simply to learn. That seems fitting. Tonight, perhaps as you rest comfortably supported by one of the better surfaces currently available, consider how unusual that support really is. A stable rocky crust, moderate gravity, manageable air, liquid water nearby, temperatures compatible with blankets. These are luxuries, not defaults. Elsewhere, there are worlds where no one stands because standing is the wrong concept entirely. And yet they are no less magnificent for it. If you could not stand there, what would it feel like to fall into such a planet? There are places in the universe where falling is not a brief event. On Earth, falling is usually a short and rather decisive experience. You trip on a stair, miss a step, drop from a ladder, or in dreams drift downward in that peculiar slow-motion way the mind enjoys. Gravity here tends to keep things practical. Distances are modest. Atmospheres are familiar. Ground is committed to punctual arrivals. But on a world like WASP-193b, falling could become an extended journey through layers of gas, heat, pressure, and gradually escalating consequences. Because there is likely no sharp surface waiting below, no pavement, no hillside, no patch of grass helpfully softening the narrative. Instead, there is atmosphere stretching downward across immense depth. So what would it feel like to fall into such a planet? As always, we must begin with an impossible disclaimer. No human could simply leap into WASP-193b unaided and provide a review afterward. The environment would be hostile, and the return survey would be difficult to administer. But as a thought experiment, it is a lovely one. Imagine yourself in a protective craft hovering above the visible cloud tops of this giant low-density world. Beneath you lies a broad sphere of hazes and atmospheric layers, warmed by its nearby star, swollen outward by heat and light gases. From a distance it looked almost soft. Up close, softness gives way to scale. You begin descending. At first, the sensation might feel less dramatic than expected. The upper atmosphere could be thin and extended. There may be little visual cue for movement except changing cloud textures and shifting colours. No clear entry point exists where space suddenly becomes planet. Instead, vacuum yields gradually to gas. This alone would be strange. On Earth, we like borders, shorelines, doorways, thresholds. Even airports attempt this concept. Gas giants are less cooperative. You would cross no obvious line, only increasing atmosphere. Depending on altitude, the gravity near the outer measured radius of WASP-193b may be milder than its giant size suggests, because much of the atmosphere is extended far from the centre, so the initial downward acceleration might not feel overwhelmingly fierce. But do not become smug. The planet has time. As you descend deeper, drag from the atmosphere increases. Falling through gas differs greatly from falling through vacuum. Air resistance grows, eventually limiting speed. On Earth, skydivers reach terminal velocity when drag balances weight. In a giant atmosphere, similar principles apply, though with unfamiliar densities, temperatures, and compositions. So after some acceleration, you may stabilize at a descent speed determined by gravity, atmospheric density, and shape. This means the experience could shift from plunge to prolonged sinking. You're no longer dropping toward ground, you're moving through a fluid world. That would feel less like falling into a canyon and more like descending through an endless sky that keeps thickening around you. Clouds might envelop the craft. Visibility could narrow. Light from the star above would fade into diffuse glow. Winds may buffet the vehicle. Instruments would report rising pressure. 1 bar, several bars, dozens, and onward. Pressure is one of those realities humans underestimate because on Earth it behaves so politely. Our atmosphere presses on us constantly, yet we scarcely notice. We evolved inside it. It became background. Descend into a giant planet and pressure stops being background. It becomes management. At increasing depths, the gas compresses around you. Structural loads on any craft rise. Seals matter more. Design regrets become vivid. If you were somehow unprotected, the journey would end quickly and unpleasantly long before interesting depths were reached. So let us stay inside our imaginary vessel, where engineering remains heroic. Now the temperature begins to climb. This is crucial. On giant planets, descending often means entering warmer layers. Compression heats gas. Internal heat may rise from below. Stellar heating affects upper levels. The deeper you go, the less likely you are to remain comfortable enough to compose thoughtful travel notes. Warm becomes hot. Hot becomes severe. Severe becomes a category requiring new labels. For WASP-193b, already living close to its star, upper layers may start warm by planetary standards. Deeper regions could become extreme. The craft would need cooling systems, pressure resistance, and perhaps a therapist. There is another sensation to imagine: motion without arrival. On Earth, falling carries expectation. You know something lies below. Even if hidden by fog, ground exists somewhere in the story. On a gas giant, that certainty weakens. There may be a dense core deep below, but not at any reachable depth for ordinary technology. Instead, the atmosphere grades continuously into denser and stranger states. At what point have you arrived? When clouds end? When pressure reaches a chosen value? When hydrogen behaves oddly? When your dashboard begins expressing concern? There is no universal answer. So psychologically, falling into such a world might feel uncanny. You keep descending, yet destination remains abstract. The sky above darkens, the atmosphere thickens, the craft creaks, and still there is no floor. Wind would likely be another major part of the experience. Close-in giant planets can host powerful circulation as heat moves from dayside to nightside. Jet streams may race at extraordinary speeds. Turbulence could shake the craft violently depending on altitude and weather systems. Earthly storms are local inconveniences. Planetary storms on giant worlds can be continental in scale, sometimes larger. Imagine descending through a weather system the size of nations. That would focus the mind. Sound, too, would change. In thin upper layers, perhaps little would be heard beyond machinery. In denser gas, vibrations travel differently. Buffeting winds, structural groans, engine corrections, deep rumbles of atmosphere might fill the cabin. Not silence, not calm. A long mechanical conversation with fluid dynamics. Now, let us consider buoyancy. As the atmosphere grows denser, your craft may eventually become more like a submarine than an aircraft. In sufficiently dense gas, objects can float if their average density is lower than surrounding fluid. So a descent could transition from falling to sinking to hovering, depending on design and conditions. That is wonderfully strange. The same vehicle might begin like a capsule, then behave like a balloon, then like a submersible in gas. Worlds unlike Earth demand flexible identities. Deeper still, matter becomes less intuitive. Under enormous pressures, hydrogen may enter exotic states, potentially conductive, compressed, no longer resembling everyday gas. The boundary between atmosphere and interior becomes philosophical rather than scenic. By then, falling through sky has become moving through planetary material. At such depths, any realistic craft we can imagine today would likely fail. Pressure and heat win eventually. The universe is patient about this. Would you feel weightless at any point? Not exactly. Falling freely in a vacuum can create weightless sensation, but with atmospheric drag and controlled descent, forces become more complicated. Depending on craft motion, acceleration, turbulence and support systems, you might feel periods of lightness, jolts, pressure in the seat, sideways forces and persistent motion cues. It would likely be less graceful than cinema suggests. There is also the emotional side. At first, curiosity, then awe, then fascination with instruments, then concern about pressure readings, then renewed respect for rocky planets. Perhaps that is one reason Earth feels so precious. We rarely appreciate how luxurious a solid surface is until imagining its absence. To stand, to sit, to place a cup on a table without calculating atmospheric shear forces. These are privileges. Worlds like WASP-193b remind us that much of the cosmos is not built for feet. It is built for equations. Still, there is beauty in the descent. Imagine looking upward through layers of haze and seeing the star as a dim, bright disk through atmospheric bands. Imagine colours shifting with chemistry and pressure. Imagine clouds stacked in unfamiliar decks. Imagine lightning, perhaps, immense and distant, illuminating vast volumes of gas. A place hostile to bodies can still be generous to imagination. Would you ever stop falling? Eventually, yes, in practical terms. Drag, buoyancy, controlled propulsion, or catastrophic structural disagreement would end the simple notion of falling. But if you mean, would you reach a clean surface where descent concludes neatly? Probably not. Not in any satisfying human sense. You would transition through states, not arrive at a floor, and that may be the most alien part of all. We like endings. Gas giants prefer gradients. Tonight, as you rest on a dependable planet whose downward journeys are usually short and whose surfaces continue their excellent work, perhaps take comfort in how rare and convenient that arrangement is. Elsewhere, there are worlds where down is a long story, where falling becomes exploration, where the atmosphere is not what lies above life, but the world itself. Elsewhere in the galaxy, strange company waits. By the time astronomers confirmed WASP-193b as one of the lowest density giant planets known, it had already joined a growing club of worlds that once sounded too odd to be real. This is one of the quiet revolutions of modern astronomy. The night sky used to be a place of stars, constellations, and speculation. Now it is also a census of surprises. Every few years, another planet appears that makes scientists pause, check the data, and politely revise expectations. Not because nature is breaking its own rules, but because our rules were often based on a sample size of one solar system. That is a dangerous place from which to generalize. If an alien civilization studied only its own neighborhood, it might conclude all planets come with names impossible for humans to pronounce, and moons shaped like decorative turnips. Local evidence can mislead. So let us meet some of the other worlds that once seemed impossible. A natural place to begin is the family of super puffs, because WASP-193b is not alone in being suspiciously airy. The system around Kepler-51 became famous for hosting planets with extremely low densities. Several of its planets appeared so large for their masses that astronomers described them as cotton candy-like long before WASP-193b entered public conversation. These worlds helped establish that low-density giants were not measurement flukes. They were a real category that mattered enormously. One bizarre planet can be dismissed as a one-off curiosity. Several bizarre planets demand theory. Then there are the hot Jupiters. Before the first confirmed exoplanets around Sun-like stars were found, many astronomers expected giant planets to live mostly in outer systems, as Jupiter and Saturn do here. That seemed sensible. Giant planets need lots of material, cooler regions, and room. Then along came 51 Pegasi b in the 1990s, a giant planet orbiting scorchingly close to its star in only a few days. This was a shock, not because it violated physics, but because it violated prevailing expectations. It launched the entire hot Jupiter category and forced planetary migration into mainstream theory. Sometimes one planet can rearrange a field. Next, we meet lava worlds. Consider 55 Cancri e, a rocky super-Earth orbiting so close to its star that surface temperatures are thought to be extreme enough for molten rock environments. Depending on models and observations, the planet may host lava oceans or at least vast molten regions. A world where rock behaves like weather. That sentence would have sounded fictional not long ago. Then there are worlds so dark they absorb most incoming light. TRES-2b became famous for reflecting remarkably little starlight. It was described as darker than coal, darker than many familiar substances, glowing faintly red only because of its heat. A giant world almost swallowing light. Not supernatural. Simply atmospheric physics with dramatic public relations. Now let us turn to density in the opposite direction. Some exoplanets appear astonishingly dense, suggesting large iron cores or unusual internal compositions. K2-229b has been compared in some studies to an oversized version of Mercury, potentially rich in metal relative to silicates. So while WASP-193b spreads modest mass across huge volume, other worlds compress heavy material into compact seriousness. The galaxy appreciates variety. There are also planets with years so short they seem rushed. K2141b orbits in mere hours. On such worlds the star looms close, temperatures soar, and the concept of a calm season becomes rather optimistic. Imagine celebrating New Year several times in a weekend. This is why one must be careful bringing Earth calendars into space. Some planets orbit not one star but two. Kepler 16. B famously circles a binary star system, evoking fictional twin sunset imagery that turned out to be entirely compatible with orbital mechanics. These circumbinary planets reminded us that stable worlds can exist in systems once thought too dynamically messy. Nature often manages complexity better than our first instincts expect. There are planets on wildly elongated orbits too. HD 80,606b follows a dramatically eccentric path, swinging close to its star and then far away. During close approaches, temperatures can rise sharply. Seasons there are not gentle transitions, but dramatic episodes. Some worlds do not do moderation. And then there are rogue planets, objects not clearly bound to any star at all. These wandering worlds drift through interstellar darkness, perhaps ejected from young systems during chaotic gravitational encounters. A planet with no sunrise, no ordinary year, no host star dominating the sky. Lonely, perhaps, though loneliness may be an Earth-centered interpretation. Still, a free-floating planet would once have sounded absurd. Now it is plausible and increasingly supported by observations. What ties all these examples together is not merely weirdness, it is humility. For centuries, we built our mental picture of planets from the few worlds we could observe directly, those in our own solar system. It was a magnificent starting point, but still a starting point. Then exoplanet science began revealing that our neighbourhood is one arrangement among many. Some systems place giants close in, some build common planet types we do not have here, such as mini-Neptunes. Some create low-density superpuffs, some forge scorched rocky worlds with lava surfaces, some allow planets to circle two stars, some fling planets into darkness. The word planet has grown larger. That is one reason WASP-193b matters beyond its own measurements. It is part of a broader pattern. The universe repeatedly exceeds our templates. When people say a planet shouldn't exist, what they often mean is, it doesn't fit the simplest version of what we thought planets were. That sentence has become increasingly common and increasingly useful. Because each mismatch improves theory. Hot Jupiters taught us migration. Superpuffs teach us atmospheric inflation and retention. Lava worlds teach us about extreme rock behaviour and star-planet interaction. Dense, iron-rich worlds test formation and collision models. Circumbinary planets test orbital stability. Rogue planets test system chaos and ejection histories. Every oddball world is also a textbook. There is something wonderfully democratic about this. The universe does not reserve insight only for elegant systems. Messy systems teach plenty. Extreme systems may teach more. Even public nicknames help. Cotton candy planets, hell worlds, eyeball planets, diamond planet headlines, sometimes over-enthusiastic. These names capture imagination, and imagination often leads people toward the deeper science beneath them. A child who hears about a planet made of lava may later learn spectroscopy. An adult amused by a cotton candy giant may discover density and orbital mechanics. Wonder is a doorway. It need not be solemn to be valuable. Another quiet lesson from these impossible planets is that habitability cannot be assumed from category labels alone. Planet tells you less than many think. A planet may be frozen, roasted, crushed, gaseous, irradiated, tidally locked, stripped, or temperate. World is a broad word. Earth is one subtype, not the default. That perspective can make our own planet feel rarer and more precious. Solid ground, moderate climate, liquid water, breathable air, magnetic shielding, long-term stability, and a star neither too violent nor too dim. These are not guaranteed features of planets generally. They are blessings of a specific case. So while we enjoy the absurdity of worlds like WASP-193b, we may also quietly appreciate the dependable flaw beneath our feet. Tonight, perhaps as your room settles into calm and familiar gravity continues its excellent work, imagine the galaxy filled with places no travel brochure could describe sensibly. A dark giant reflecting almost nothing, a molten world with rock weather, a twin sunset planet circling two stars, a wandering orphan planet between suns, a balloon-like giant so light it embarrasses intuition, all real possibilities, all reminders that normal is local. Sometimes the most useful things in science are the ones that refuse to behave. A clock that runs strangely teaches the watchmaker where friction hides. A bridge that sways unexpectedly teaches the engineer where forces were underestimated. A recipe that collapses in the oven teaches humility, patience, and occasionally the need to read step 3 more carefully. In astronomy, a planet like WASP-193b plays exactly that role. It is not valuable merely because it is odd. It is valuable because its oddness points to missing understanding. That distinction matters. There is a temptation to treat unusual discoveries as entertainment, as if the universe occasionally releases novelty products to keep us interested. A cotton candy planet, a lava world, a giant orbiting 2 stars. Delightful headlines, certainly. But beneath the charm lies something deeper. Every object that does not fit expectation is a pressure test for theory, and pressure tests are how knowledge becomes sturdier. So what does WASP-193b teach us about the universe? First, it teaches that nature does not care about our tidy categories. For a long time, Our understanding of planets was built from the solar system. We had rocky inner worlds, giant outer worlds, icy distant bodies, and a few moons with flare. It was a beautiful arrangement, coherent and familiar. Then exoplanets arrived. They brought hot Jupiters, mini Neptunes, super Earths, super puffs, circumbinary worlds, rogue planets, and objects that seemed determined to confuse PowerPoint presentations. WASP-193b belongs to that lesson. The universe contains more planetary possibilities than one neighbourhood could reveal. This is important far beyond astronomy. Human beings often mistake local patterns for universal truth. We assume what surrounds us is standard because it is familiar. Nature repeatedly disagrees. Second, this planet teaches us that appearance can mislead. Large does not necessarily mean massive. Giant does not necessarily mean dense. Impressive silhouette does not guarantee heavy substance. WASP-193b looks giant in radius, yet its density is extraordinarily low. Much of its measured size may come from an expanded atmosphere rather than compact bulk. That sounds like planetary trivia, but it reflects a broader scientific principle. Measurements must be interpreted carefully. A single visible property rarely tells the whole story. Brightness does not equal distance. Size does not equal mass. Loudness does not equal correctness. The last one is less astronomical but still useful. Third, WASP-193b teaches that systems are shaped by relationships, not isolated traits. You cannot understand this planet by looking only at the planet. You must consider the host star WASP-193. Its radiation heats the atmosphere, its gravity influences tides, its size helps determine the planet's measured radius during transit, its age helps constrain planetary history, its chemistry may hint at formation conditions. The planet's story is intertwined with its star. That is common throughout the universe. Context matters. Objects become what they are partly through interaction. Stars shape planets. Galaxies shape stars. Environment shapes chemistry. History shapes present form. Even on Earth, nothing develops alone. Fourth, it teaches that change may be ongoing. Many people imagine planets as static spheres, formed once then simply existing. Yet worlds evolve continuously. Atmospheres escape. Orbits migrate. Interiors cool. Radii contract. Stars brighten with age. Tidal interactions alter motion. WASP-193b may be inflated now and different later. We may be observing a temporary phase in a long planetary biography. This is a profound shift in perspective. The universe is not a museum of finished objects. It is a workshop of processes. Everything is in motion somewhere, even when it looks still. Fifth, it teaches us the value of indirect knowledge. No human has visited WASP-193b. No probe has sampled its winds. No tourist has complained about the weather. Yet through tiny dips in starlight and subtle stellar wobbles, we infer its size, mass, density, orbit, and likely atmospheric behaviour. That is astonishing when you pause long enough to feel it. Light left a distant star. Some of it passed through or around a planet's atmosphere. It travelled across space. Instruments on Earth recorded tiny changes. From that, minds reconstructed a world. Science often works this way. We learn not by touching everything directly, but by reading consequences carefully. Tracks in snow reveal an animal. Spectra reveal chemistry. Ripples reveal hidden objects. Silence reveals distance. Small signals reveal enormous truths. WASP-193b reminds us how much can be known through patience and precision. Sixth, it teaches humility about models. Models are not failures when they need revision. They are tools doing their job. A model says, given what we know, here is what we expect. Then nature responds, interesting. Here is what I actually did. That conversation drives progress. If every planet matched early expectations perfectly, astronomy would be simpler but poorer. Surprises expose blind spots. They reveal neglected mechanisms, missing variables, or overly narrow assumptions. A strange world is not an embarrassment to science, it is an invitation. Seventh, it teaches that common ingredients can create uncommon outcomes. Hydrogen and helium are ordinary by cosmic standards. They are the most abundant elements in the universe. Yet arranged under certain masses, temperatures and orbital conditions, they become a giant low-density world that sounds fictional. This happens everywhere in nature. Carbon becomes graphite, diamond, soot, living tissue and libraries. Water becomes ice, steam, clouds, rivers, glaciers and weather. The same ingredients can yield radically different structures depending on conditions. So when we ask what the universe is made of, composition is only half the question. Arrangement matters just as much. Eighth, it teaches that rarity is relative. When something unusual is discovered, we often ask whether it is unique. But uniqueness depends on how much of the sky we have searched, with what sensitivity, and for how long. There may be many planets like WASP-193b still waiting to be found. Perhaps they are uncommon. Perhaps they are a transitional stage many worlds pass through briefly. Perhaps they hide in data already collected. The universe is larger than our sample sizes. That is always worth remembering. Ninth, it teaches gratitude for Earth without diminishing wonder elsewhere. A world with no clear surface, extreme heating, and tenuous grip on a bloated atmosphere can be fascinating. It can also remind us how comfortable our own planet is. Stable ground, moderate temperatures, breathable air, liquid water, long-lived climate windows, predictable days and years. These are not baseline planetary settings. They're a fortunate configuration. Exoplanets do not reduce Earth's beauty, they sharpen it. And finally, WASP-193b teaches that curiosity scales. The same instinct that makes a child ask why bubbles float can eventually lead humanity to ask why a giant planet has the density of cotton candy. That continuity is lovely. Wonder begins small, then grows. A person looks up at stars. Later people build telescopes. Then instruments detect tiny periodic dimming. Then equations estimate density. Then the world gains a nickname. Then someone listens to a calm video before sleep wondering how any of this is possible. Curiosity survives across generations. There is comfort in that. Tonight, perhaps while your room remains pleasantly uninflated and your local atmosphere continues its dependable service, consider how much we have learned by refusing to stop asking questions. A distant star flickers. We investigate. A giant airy world emerges from data. We ask why. The answer is incomplete, so we keep going. That may be the most important lesson of all. Knowledge is not built by arriving once and for all. It is built by returning, measuring again, improving, and staying interested. WASP-193b teaches physics, planetary science, and humility. But perhaps most of all it teaches persistence. Even after thousands of discoveries, the universe still has the nerve to seem new. You might think that after centuries of astronomy, after observatories on mountains, telescopes in orbit, spacecraft crossing the solar system, computers processing oceans of data, and scientists armed with equations serious enough to frighten furniture, surprise would begin to fade. Surely by now we would have the general idea. Surely the cosmos would settle into categories, reveal its habits, and stop producing worlds that sound invented. Yet it does not. Instead, just when a pattern starts to feel comfortable, another exception arrives. A planet too hot for intuition. A moon with an ocean under ice. A black hole larger than expected. A star behaving strangely. A giant world like WASP-193b with the density of spun sugar. Why does this keep happening? Part of the answer is simple. The universe is not small. This sounds obvious, but it deserves more respect than it usually receives. Human intuition evolved in a tiny local environment. We learned from forests, weather, stones, rivers, seasons, and the nearest visible lights in the sky. We did not evolve to feel comfortable with billions of galaxies, trillions of stars, or planetary systems, assembled under countless combinations of chemistry and chance. So when we generalize quickly from familiar examples, we're doing what minds naturally do. And when the universe contradicts us, it is doing what a vast sample size naturally does. If you study only one tree, you may think all trees bend the same way. Study a forest across continents, climates, soils, and ages, and variation becomes the rule. The cosmos is the largest forest imaginable. That alone creates surprise. For most of history, humanity knew only the planets of our own solar system. It was a rich collection: rocky inner worlds, giant outer worlds, icy moons, rings, storms, comets, and enough wonder to occupy many lifetimes. But still, it was one system, one arrangement around one star. Then exoplanets entered the story. Suddenly we learned that planets can orbit two stars, skim their suns in days, drift alone through darkness, swell into superpuffs, burn into lava worlds, or cluster in configurations our system never attempted. The surprise was not that these things existed. The surprise was that we had mistaken local familiarity for cosmic standard. This happens repeatedly in science. Earth once seemed central, then one planet among many. Our sun once seemed singular, then one star among billions. Our galaxy once seemed the universe, then one galaxy among more than imagination comfortably handles. Each expansion of perspective reduces certainty and increases wonder. That is a healthy trade. Another reason the universe keeps surprising us is that simple rules can generate complex outcomes. Gravity is conceptually simple. Mass attracts mass. Yet from that rule emerge stars, galaxies, tides, black holes, spiral arms, orbital resonances, planetary migration, and giant atmospheric worlds with strange densities. Chemistry follows understandable principles. Yet from chemistry come minerals, clouds, oceans, atmospheres, proteins, forests, and coffee. Basic ingredients do not guarantee basic results. A few rules, repeated across time and scale, can produce extraordinary diversity. You see this on Earth as well. The same atoms become granite, coral, wings, rain, paper, and people. Why should planets be simpler? WASP-193b is a fine reminder of this principle. Hydrogen, helium, gravity, stellar heating, orbital dynamics, time. Nothing exotic in the ingredient list. Yet combine them under the right circumstances and the result is a giant world so low in density that astronomers reach for carnival metaphors. Ordinary rules, unexpected outcomes. There is also the matter of incomplete data. We often imagine science as a finished encyclopedia gradually updated with decorative footnotes. In reality, science is usually mid-conversation. We know much, but never all. Our current models are best approximations built from available evidence. As tools improve, hidden details emerge. Better telescopes reveal fainter worlds. Sharper spectroscopy reveals atmospheric molecules. Longer monitoring reveals subtle orbits. More discoveries reveal broader populations. When the window widens, surprises enter. This is not because old science failed. It is because better vision changes maps. Think of ancient coastlines gradually refined by exploration. The first maps were not foolish. They were limited by reach. So are we. Another source of surprise is timescale. The universe has had about 13.8 billion years to experiment. Stars formed, died, enriched space with heavier elements, seeded later stars and planets, triggered new generations, merged, migrated, collided, cooled, and transformed. Given enough time, even rare arrangements become inevitable somewhere. If a planetary architecture has a 1 in a million chance, and there are vast numbers of systems, then many such worlds may still exist. Rarity at small scale becomes abundance at cosmic scale. That can be difficult for human intuition, which is more comfortable with neighbourhoods than galaxies. There is also selection bias, one of science's less glamorous but highly useful reminders. We notice certain things more easily than others. Close giant planets are easier to detect than distant small ones. Transiting planets are easier to confirm than non-transiting ones. Bright stars are easier to study than dim ones. So early discoveries often reflect what instruments can see best, not necessarily what is most common. This means surprise sometimes comes in two waves. First, strange, easy-to-detect objects dominate headlines. Later, improved tools reveal quieter but perhaps more common realities. The universe may not be changing. Our access is. WASP-193b, for instance, is surprising partly because inflated close-in planets are detectable through transits and stellar wobble. There may be equally fascinating categories still hidden because they whisper instead of shout. That possibility is delightful. It means mystery remains. There is a philosophical reason surprise persists too. Human beings crave patterns. Pattern recognition helped our ancestors survive. Notice tracks, weather signs, seasons, faces, danger. Minds that linked clues quickly often did well, but the same strength can oversimplify. Once we detect a pattern, we want to stabilize it. We say, "Ah, yes, planets are like this." Then the universe replies, "Some are." Continue. This tension between pattern and exception is not a flaw. It is the engine of learning. Pattern gives prediction. Exception gives growth. Without pattern, nothing is understandable. Without exception, nothing improves. So perhaps the universe keeps surprising us because surprise is how finite minds meet infinite variety. There is comfort in that idea. You do not need complete certainty to participate in understanding. You only need enough curiosity to revise. Another lovely reason for ongoing surprise is that we ourselves keep changing the questions. Ancient observers asked where stars moved. Modern astronomers ask what exoplanet atmospheres contain. Future researchers may ask how weather systems behave on superpuffs, how biosignatures appear on ocean worlds, or how planetary systems evolve across galactic environments. New questions create new surprises. The universe may contain endless facts, but which ones astonish us depends partly on what we are ready to notice. Tonight, perhaps in a room lit softly enough that ordinary objects look gentler than by day, it may be soothing to remember that not knowing everything is not a defect. It is room for discovery, room for better questions, room for the next impossible-seeming world to appear in data and quietly rearrange confidence. A distant planet with a 6-day year, a giant with the density of cotton candy, a world no one expected in exactly that form, and yet there it is. Perhaps the deepest reason the universe keeps surprising us is that reality was never built to satisfy expectation. It simply unfolds according to its own conditions, histories, and laws. We are the ones catching up. That sounds humbling, but also generous. It means there is always more to learn. Always another edge of the map. Always another measurement waiting in starlight. Tonight we travel to a place that seems as though it should have remained imaginary. Not because it was magical, not because it required breaking physics, not because the universe briefly abandoned professionalism, but because WASP-193b sits so far outside ordinary instinct that the first reaction is often laughter, followed closely by wonder. A giant world, broad as the great planets we know. A year lasting only days. An atmosphere stretched outward by heat and lightness. A density so low that scientists reach for cotton candy to explain it. And somehow, through all of that, entirely real, measured in starlight, weighed in motion, understood piece by piece across a gulf of space no human body has crossed. There is something deeply calming about discoveries like this. At first that may sound strange. Why should a bizarre, distant planet feel soothing? Perhaps because it reminds us that reality is larger than the boundaries of our routine. Most days are built from practical scales. Rooms, schedules, weather, meals, tasks, the same roads, the same screens, the same lists waiting with suspicious confidence. Those things matter. They make life function. But they can quietly shrink the imagination if we never step outside them. Then astronomy opens a window. Beyond errands and inboxes, there are stars with worlds unlike anything nearby. There are planets with no surface to stand on. There are atmospheres deeper than oceans. There are years shorter than weeks. There are systems whose mere existence asks us to loosen certainty. That widening can feel like relief, not because our lives become smaller, but because our perspective becomes larger. WASP-193b also offers a gentler lesson. Not everything solid looking is solid. Not everything large is heavy. Not everything familiar from a distance remains familiar up close. This is true in astronomy, but perhaps it echoes elsewhere too. Many things in life look simpler from afar than they are in detail. Many judgments soften when examined closely. Many assumptions turn airy once measured carefully. Science trains a useful humility. Look again, measure twice, leave room to be surprised, and if surprise arrives, welcome it. Somewhere far beyond our sky, this inflated world continues its quick orbit around WASP-193. It does not know we named it. It does not know we compared it to carnival sugar. It does not know papers were written, models revised, or sleepy listeners imagined drifting through its clouds. It simply continues, round and round, receiving starlight, holding its atmosphere as best it can, existing in that calm way celestial things often do. There is peace in that too. The universe is full of motion, yet so much of it is steady motion. Planets orbit, stars rotate, galaxies turn, light travels, seasons return. Even change often follows patterns. We sometimes confuse unpredictability with chaos, but many surprises emerge from orderly systems observed more carefully. A strange planet still obeys gravity. A bizarre orbit still follows mechanics. An impossible-seeming world still belongs to law. That can be comforting. Reality may be wider than expected, yet it is not senseless. As your own evening settles further now, perhaps notice the contrasts around you. Your floor is firm, your atmosphere mild, your gravity familiar, your year comfortably long. No tidal locking in the bedroom, one hopes. No hydrogen envelope requiring explanation. No nearby star inflating the furniture. These ordinary blessings are easy to miss until compared with the alternatives. Exoplanets often do that for us. They make Earth feel less ordinary, without making it less home, and perhaps that is one of astronomy's kindest gifts. It lets us admire distant strangeness while appreciating nearby normality. We do not need to live on a super puff world to learn from it. We only need to listen. A flicker in starlight became a story. A tiny wobble became mass. A transit became radius. Numbers became density. Data became wonder. Then wonder became perspective. That transformation is one of the most beautiful things humans do. We take faint signals from darkness and turn them into understanding. Slowly, imperfectly, repeatedly, together. If your thoughts are still moving, let them move more gently now. Imagine that distant system once more. A star glowing in black space, a large pale world circling close, its upper atmosphere broad and soft-edged against the light. No sharp shoreline, no mountains visible, just layers fading outward into the dark, floating through the soft edges of reality. And perhaps that phrase belongs not only to planets. Much of life is lived near soft edges, between certainty and mystery, between what we know and what we are learning, between the measurable and the meaningful, between today's ordinary knowledge and tomorrow's surprise. We do not stand on firm ground all the time. Sometimes we drift through questions. Sometimes we hover inside incomplete answers. Sometimes we discover that what seemed impossible was merely unfamiliar. That is not failure. That is growth. So tonight, if the day has been heavy, let this airy world carry something for you. Let scale loosen worry. Let distance soften urgency. Let curiosity replace noise for a little while. Let the mind wander somewhere no footsteps can go. And when sleep comes, as all good orbits eventually do, let it arrive without resistance. The star can keep burning. The planet can keep circling. The equations can wait until morning. For now, you have done enough. Thank you for spending this quiet journey here at Science for Sleep. Wherever you are in the world, whatever time it may be in your corner of Earth, I'm glad we crossed paths tonight. Rest well. And somewhere far away, WASP-193b continues drifting through starlight, light as intuition never expected, patient as the universe always is.